said, if you educate a man, you educate an individual. But if you educate a woman, you educate a nation. Yes, it is true. Having belief in these great words, our college, over the period of time, emerged as a premier women's institution in Andhra Pradesh. At present, 34 regular 40 contract lecturers, 6 guest lecturers are working to meet the academic activities of our college. The college offered 21 programs in BA, BCom, BSc, 4-year degree honors. The present strength of the students is more than 2,700. The college got accredited with A+ grade by the NAC, and it was conferred with autonomous status by UGC. And the implementation of autonomous status is scheduled to commence from this academic year, that is 2024-25. Education is the key that unlocks the golden doors to freedom. Yes, I strongly believe these words. I am proud to say that our college is dedicated to ideal of making better women of its students by imparting good instructions to achieve academic excellence and good values to mold their character and personality. Curricular, co-curricular, and extracurricular activities are encouraged to ensure comprehensive development of the students. Today, I am proud that our physics department is organizing this webinar to ignite the research knowledge in the young minds and also for the benefit of the future generation. In this regard, I would like to extend my warm congratulations to the head of the Department of Physics and the entire staff of the Physics Department. The main theme of the webinar is renewable energy sources and applications. I am proud that the objective of the webinar was chosen by the Physics Department because we require a sustainable energy source to mitigate our energy crisis. Our future generation must strive hard for the innovative renewable technologies for the development of a nation. I hope this webinar will showcase the latest advancements in renewable energy technologies, focusing on solar, wind, and bioenergy. I trust that all the attendees will gain knowledge towards research activity, including improved efficiency and novel materials that are driving the future of sustainable energy. I wish the organizers of the webinar and all the participants good luck and have a good day. Thank you very much.
Thank you, madam. Thank you for your valuable message to all the participants of today's webinar. In the next few minutes, we have the exciting lineup of dynamic speakers who will share their expertise on renewable energy sources and applications. We believe the insights and knowledge shared by the resource persons here will be valuable to each one of you. I request Dr. D. Uma Maheshwari to introduce our today's excuse me. I would like to call upon our HOD Madam, the Organizing Secretary, Dr. C. Uma Devi, to express the main objectives of this webinar. Madam, please. Om Namo Venkatesaya. A very good morning to you all. I am Dr. C. Uma Devi, HOD of Physics and the Organizing Secretary of this one-day international webinar. I am very happy to welcome our distinguished Executive Officer Shyamalarav Garu, Joint Executive Officer Gautami Madam Garu, Devasthanam Educational Officer Nagaraj Nayadu Garu, and our beloved Principal Madam, who is Dr. T. Narayanamma Madam Garu, who is also the convener of this program. Our today's resource persons, my dear faculty members and participants, a warm welcome to you all. I would like to give a brief description of our department. The Department of Physics is established in 1952. It is a dynamic and innovative part of the college. It offers BSc honors in physics,
The department's vision is to ignite enthusiasm and passion in the study of physics. It is committed to provide quality education with a strong emphasis on learning by doing and motivate students towards research in physics and interdisciplinary areas. Department encourages collaboration with reputed academic institutions and also promotes scientific culture through co-curricular and extracurricular activities. Our department is always keen, committed, amped up in imparting the knowledge to the students in the field of physics by arranging seminars, field visits, guest lectures, and so on. We are arranging this type of webinars in order to motivate our students towards the novel technologies arising around the world. Now, I am glad to say that the objective of this webinar is that renewable energy systems have rapidly become more efficient and cheaper over the past 3 decades. This webinar will showcase latest advancements in the renewable energy technologies, focusing on solar, wind, and bioenergies. The participants will gain insights into cutting-edge research, including improved efficiency and novel materials that are driving the future of sustainable energy. A key discussion point will be the integration of renewable energy into existing power grids. Experts will address technical challenges, economic implications, and regulatory frameworks necessary for a smooth transition to a sustainable energy future. The webinar will also explore the environmental and social impacts of renewable energy adoption. Case studies of successful projects will be presented, highlighting the role of renewable energy in promoting global sustainable development. We are glad to have today's well-expertised resource persons in this field, especially in fabrication of solar cells and thin film batteries. I am sure the participants will gain knowledge in the field of renewable energy through this webinar. Thank you for giving me this opportunity. Thank you, one and all.
Thank you, madam. Thank you for your brief description about the department. I request Dr. D. Uma Maheshwari to introduce our today's resource person, Dr. U. Tirupati from South Korea.
Om Namo Venkateshaya. Good morning, everyone. Today we have the privilege of being in the presence of true visionary person in the field of environmental sustainability. Dr. Uppala Tirupati, very young and dynamic person. Dr. Tirupati, now working as the assistant professor in the Department of Electronic Engineering, Agnam University, South Korea. It gives me great pleasure and an opportunity to introduce him as our today's resource person of the webinar. Dr. Tirupati has a great interest in the field of renewable energy materials, especially in thin film solar cells and photoelectrochemical water splitting. He worked as the research professor in the Department of Electronic Engineering, University of South Korea. He received his postdoctoral fellow from the Center for Optoelectronic Materials and Devices, Korea Institute of Science and Technology, Seoul, South Korea. Dr. Tirupati has more than 20 years of research experience in the field of solar cell fabrication. He has good experience on first one is growth of binary, ternary, and quaternary compound semiconductor thin films by co-evaporation, two-stage process, that is thermal evaporation, chemical bath deposition, sulfurization, chemical spray pyrolysis, and chemical bath deposition technique. The second one is fabrication of compound semiconductor thin film heterojunction solar cells. Dr. Tirupati, another research skill is that he is expertise in the operation, maintenance, and troubleshooting of vacuum systems. He has good experience on GI XRD and powder X-ray diffractometer micro-Raman spectroscopy, scanning electron microscopy, and energy dispersive X-ray spectroscopy, UV visible NRI spectrometer, that is which represents spectral transmittance and reflectance, Hall effect for electrical properties, solar simulator for IV measurements of solar cells. Dr. Chalpati has fabricated copper antimony disulfide based thin film solar cells with the efficiency of 2.5%. He is also expertise in the electrode deposition of bright nickel, block nickel, and black chrome selective surfaces for solar thermal applications, microfabrication of PBS-based IR detectors using photolithography, lift-off, etching, etc. techniques. He was the recipient of IUSSTF and DST BASc internship to carry out research work at University of Utah, USA. To his credit, he published nearly 50 peer-reviewed research papers on solar cell characterization and fabrication. This is all about brief introduction of our today's resource person, Dr. U. Chalpati. Thank you for giving this opportunity. Thank you, one and all.
Thank you, Uma Maheshwari. So without any further ado, let us start the program and dive into the world of renewable energy sources and applications. Welcome, Dr. Chalpati, sir.
நம்ம டன் வச்சுனான்னு போய் கேளுங்க. ரெண்டு குத்துது ஒண்ணு.
Hello everyone. We can't hear anything here.
జ్యోతి మేడం. జ్యోతి
ప్రెజెంటేషన్ స్లైడ్ కనిపిస్తుంది.
Sorry, audience, please excuse me for the some technical issues. We are unable to connect Dr. Chalapati. So I request our another resource person, Dr. P. Jeevan Kumar from University of Japan. And before that, I would like to introduce my colleague, Dr. G. Lakshmi Sandhya, faculty in our department. So G. Lakshmi Sandhya will give the brief description and introduce our resource person, Dr. P. Jeevan Kumar. Sandhya.
ఇక్కడ highlight చేయాలి.
Namo Venkateshaya. Om Namo Venkateshaya. Good morning to one and all. Today I am extremely happy to introduce our resource person, a visionary leader in the field of renewable energy sources and materials. That is Dr. P. Jeevan Kumar, Assistant Professor, Department of Engineering, Kitami Institute of Technology, University of Japan. Dr. Jeevan Kumar has deep interest in the research field like solid-state batteries, material science, electrochemistry, and particle technology. It's really a proud moment for me to say that Dr. P. Jeevan Kumar was the alumni of SV University, Tirupati. He was awarded PhD degree from SV University under the guidance of Professor OMD Hussain, Department of Physics, SV University, Tirupati. Really, I feel myself proud that I am also his co-research scholar during his PhD studies. We worked together under the same research supervisor. It is very happy to me to introduce. And today I am glad to introduce him as the resource person of today's webinar. Dr. Jeevan Kumar did his postdoctoral fellowship in the Research Institute of Electronics, University of Japan. Now he is working professor in the Kitami Institute of Technology, University of Japan. And two times he was awarded the Best Young Ceramicist Award in 2016 and 2018 from University of Japan and University of South Korea. In addition to this, he received 3 more Best Presentation Awards during his PhD studies. He has nearly 15 years of research experience in this field. To his credit, he published 32 research papers in peer-reviewed journals and 13 international proceedings. Sir, we are very lucky to have you here today. And now Sir is going to present a talk on evolution of battery technology from traditional to solid-state innovations. Once again, a warm welcome to you, sir, for this morning session. Thank you.
Thank you, Lakshmi Sandhya.
Can you able to hear me? Can you able to hear me?
Yes, sir. Yes, sir. You're audible, sir. Please go ahead.
Yeah, thank you so much.
You are audible, sir.
Yeah, how about the presentation slide?
Yeah, it's okay.
Okay then. Yeah. Now, good morning, everyone. This is Jeevan Kumar Padati. Thank you so much for giving this opportunity. I would like to thank each and every organizer for giving this opportunity, especially Jayashree Madam and Sandhya Ma'am, whom I know personally. And actually, they took so much of interest to make me to participate in this event. And I'm really happy to present some of my what is called insights related to the evolution of battery technology from traditional to solid state innovations. So before going to say that, I would like to introduce myself. And myself, Jeevan Kumar Padarte, I'm working as assistant professor at Kitami Institute of Technology. My field of expertise is material science, especially metal alkoxide derived sol gel processing. And also I'm interested, and I am working on particle technology, which is majorly concerned with what is called slurry making as well as concrete manufacturing too. And present research field topics are all solid state lithium battery I'm interested in, and especially nano coating technology of the particle, especially for, and also like polymer composites I'm interested. I'm also being part of metal air battery systems development. So these are the projects I'm working on, especially okay, sorry. Yeah. You could see that Kitami, this is a Japan map. You could see that Kitami is some ways, I'm living in this island. This is Hokkaido. Kitami is somewhere here. And you could see the aerial view of our campus. And these are my projects. I'm working on it. And these are two related to development of polymer nanocomposites. And I would like to tell about two other projects which I involved, which are the very prestigious national projects for the development of all solid state batteries. I will introduce them. What are they later? Yeah, and let me introduce some of the what is called fragrance of Kitami. Kitami is very famous for onion cropping, and it also famous for its largest producers of mint oil, which can produce somewhere around maybe above 60% it could fabricate mint oil for the world. It is supplying mint oil for the world. Majorly, this mint oil can be used for medicinal applications and all. And this is our team. And he is Professor Tomoya Ono. He is actually expert in material science, and he is one of the pioneer scientists in Japan. Okay, especially related to material synthesis, particle technology related fields. His name is Shigoto Hirai. He is working on metal air battery systems. So myself working as an assistant professor, I'm associating with this group, and this is our team. And Kitami is in winter. You could see the what is called like a trench of ice bed in Kitami. It reaches to minus 35 degrees Celsius. So they may mold it as a ice sculptures, and you could see the beautiful sculptures which last for about 6 months in winter. So this is some of the attractions of Kitami. I forgot to say that our institution in 2020 Winter Olympics have received a gold medal. One of our students have received gold medal under curling category. This is the game. Okay, we have international village very near to our university too. Yeah. This is a background I would like to say. Japan has taken the footsteps to reduce the carbon dioxide emission by the year of 2050. They are aiming to use the renewable energy resources up to 50 to 60%. They wanted to use the renewable energy resources for the power generation and making use of battery systems as well as hydrogen storage generation, ammonia methane power generation. So these are the various energy storage from power generation from renewable energy resources can be directly used for household applications as well as the industrial application. The another strategy they adopted to reduce the carbon dioxide emission is they are completely replacing the gasoline-based automobiles to plug-in hybrid electrical vehicles. Let's say simply it is hybrid electrical vehicles because it runs with the battery system as well as natural gas system. And by the year 2040, they wanted to replace all the gasoline, conventional petrol or diesel-based engines with this plug-in hybrid system. And by the year of 2050, they wanted to move forward for the complete removal of the gasoline system to make a complete EV battery, that which are fuel cell-based battery and a completely lithium-ion battery or some other new technology-based battery system. So, coming to my motivation, that Japan hypothesized that by the year of 2020, that slowly switching of liquid electrolyte-based lithium-ion batteries to solid electrolyte-based lithium-ion batteries. Right now, they are using the sulfide-based solid electrolyte batteries. The sulfides are maybe by the year of 2030 and mid-2035, probably these electrolytes can be replaced with oxide-based battery systems, and also they are working on innovation of new rechargeable batteries too. All such kind of advanced battery systems requires materials, selection of materials. So it requires particles in shape, material combination, and then coating or interface modification of these materials, and also like coating them into the roll-to-roll technology. Later, all these advanced battery technologies have its many interlinked with the interface modification. So it requires what is called band alignment and the fundamental physics concepts. And also like nano scale surface modification is required. This is some kind of material evolution and technology development is required for this one. So that means the battery development itself has its own material challenges. So that's why this has become my biggest motivation in continuing these studies. So the presentation outline majorly concerned with the introduction of batteries, but to advancement, human dependency on battery, global race in securing the strategic minerals, the opportunities related to the batteries development. Later, the presentation goes to the importance of nano coating on particle, and then how to control the particle layer structure, estimated the coating layer structure, and effect of coating structure on battery systems, and how these coatings can be useful for all solid state battery development can be introduced. Like all other great innovations, battery also started with an accidental innovation by Gavani, who started his experiment on a dead frog. By accidentally, when he was close with the static charge, he found that a sudden movement in the dead frog leg. He thinks that he named it as animal electricity that could be developed. So he in fact made his experiment right in front of the thunder also. That means his experiments have become very famous, which made jealous of some scientists, among which Alessandro Volta is one among them. Later, he disproved he disproved with a concept called electrochemical experiments. That is called where he has used two dissimilar materials in the solution medium, where he found that potential difference and the electron migration can be expected. In the name of Volta-Pyle, he developed a first battery system. Later, he proved that it's not the static charge that was actually mobilized this dead frog leg. It was the medium, that is body fluid, which is acted as an electrolyte when two dissimilar metals were connected. So the transport of charges has been the reason for it. So this is how the battery innovation has started. I'm not talking about the other ancient battery systems, but the first scientifically proved battery system was developed by Volta, which is in the early 1800s. Later, it has started the evolution of battery systems, such as lead-acid battery systems, alkaline battery systems, and which we are using still in the automobile systems. For example, lead-acid batteries we are using household applications as well as automobile systems. Alkaline battery we are using in daily appliances. Later, the journey of batteries, various batteries have started. If you look at these voltages, this main objective of the battery systems were targeting the reaching the high voltage condition. Likewise, the battery systems like nickel cadmium batteries and Thomas Alva Edison designed nickel iron battery systems, and then lithium ion battery systems, lithium sulfur battery systems, dual battery systems. Likewise, many battery systems are under research now. Majorly, they are concerned with the grid level energy storage systems. Here you could see the rough chart of their properties and their summary in the scale of lowest to highest. In such category, lithium-ion battery stood as the high amount of voltage, energy storage, and specific power densities. And in the case of its self-life also completely, believed to be highest. And later on, that so many other battery systems have also started, such as metal lead battery systems, metal sulfur battery systems, some other new type of batteries, ion-based battery systems, which are comes under intercalation and deintercalation phenomena. So by the year 2030, it is believed to that, so there might be the lithium-ion battery market reaches to nearly $120 billion US. So which requires, because of this demand for the lithium-ion battery market, each and every company would like to grab the market share of it. So each and every company, many companies have started. Each and every company here shown, they are in the race of getting patents and innovating their own technology through which they wanted to grab the market share of it. And into 2019, you could see that a reward for chemistry, battery chemistry, has been given in the recent past, in the year 2019. So let me explain how the lithium-ion battery has been developed. It was first started with the concept of Rudolf Hohmann, who proposed the intercalation chemistry. However, it was rightly adopted by the Stanley Whittingham. So he proposed a battery system called with lithium metal anode with a liquid electrolyte system, as well as a cathode of tantalum disulfide, which is of a layered structure. This layered structure is designed with a purpose that during the oxidation and reduction reactions, the lithium ion placed inside this layer structure can easily, being a part of oxidation and reduction reactions, can move from cathode to anode, anode to cathode easily. So that kind of structure was first designed by the Stanley. Later, this cathode structure, that three-dimensional layered structure, was reinvented by, in the name of lithium cobalt oxide. He introduced that material, which is not by a material scientist, he's a mechanical engineer. His name is Professor Goodenough. He replaced the tantalum disulfide cathode with lithium cobalt oxide, which is having a similar structure, that is layered hexagonal structure, through which he had increased the lithium-ion battery potential from 2 volts to 4 volts. Later, Akira Yoshino from Japan, he replaced the very common expensive lithium metal with petroleum coke, which is considerable as having the graphite-like structure. That means like he used the recycling material as an anode material, through which he maintained the same voltage. Since the commercial capability of this replacement, which was adopted by the Sony company, and was this what is called lithium cobalt oxide, graphite, and liquid electrolyte based 4-volt battery was first designed by commercialized by the Sony, and then Asahi Kasei. This is the journey of lithium-ion battery actually. Later, Akira Yoshino has hypothesized this diagram and put in front of the Japanese government. He hypothesized that by the year of 2025, most likely all the liquid-based lithium-ion battery systems can be replaced with solid-state battery systems. And by 2030, there is a huge demand for all solid-state batteries, so which is never happened. So the basic idea of this battery can also improve the market share as well as the battery energy density too. So with this idea, he proposed to Japanese government with a name called LIPTEC, lithium-ion battery technology, under the what is called government sponsored agency called New Energy Industrial Technology Development, NEDO. he named one under the NEDO. He prepared the first level project that is called solid EV. That means solid lithium-ion battery development for electrical vehicle. This is a project he proposed in the year 2018. He invited all the research laboratories who are interested to work on for the development of lithium-ion battery systems, especially solid-state lithium-ion battery systems for electrical vehicle application. And out of all the institutions, 120, nearly 119 research laboratories have been selected, and 16 industrial partners were joined in this program. Later, by the year of 2022, only 17 research laboratories have been qualified, and another 16 industrial partners have been joined, and these 17 laboratories can able to produce a technology which could be directly used for the industries for the fabrication of electrical vehicle application. So out of these 17 research laboratories, I'm proud to say Kitami Institute of Technology is one among which. Our laboratory is one of the 17 laboratories which has proven that lithium-ion batteries, all solid-state battery, which has offered the technology for the development of all solid-state battery technology. Coming to that, the major change in the future, which is basically concerned with future fuel. Future fuel, majorly it is not like gasoline-based one, which is not liquid. Majorly it could be solids, which has become the race of it. For example, it majorly starts with mining, and then refinery, and then battery cells, packaging of them, and then making it a rightful product. And then those batteries can be recycled, and then make it this vicious cycle. So for this race, majority of countries have been in race. Actually, these are the various spots. You could see that these are the spots where the refineries, various refineries have been already commissioned. Some are fully commissioned, some are majorly commissioned, where China is leading the race and Japan is following that. Korea is also in the severe race actually. So these refineries are of the major concern for the future fuel, which is the base of it. Next, securing the strategic minerals for the development of battery systems have become very popular. Then it is the survey you could see where the strategic minerals like lithium, cobalt, nickel, carbon can be abundant across the world. For example, in the case of India, that lithium reserves are recently found near Jammu and Kashmir belt, and also cobalt, nickel are abundant near what is called West Bengal region, and carbon, of course, Andhra Pradesh also is being popular of it. Of course, Telangana and Andhra Pradesh. And there are other minerals also which are equally important. For example, tellurium, tungsten, and such kind of minerals are also available, also actually found in the very close to Gujarat to what is called like Jammu and Kashmir belt. And India's stand for this securing these strategic minerals also started in the year 2019, just before the COVID system. That is like NALCO, that means National Aluminium Corporation, and then MECL and then HCL have become a consortium and made a name called KABIL. KABIL means Khanij Bidesh Bharat, Khanij Bidesh India. So in major goals of this KABIL is identifying and acquisition of these strategic minerals across the world and procuring them to India, and then securing them somewhere in India and those deposits, and then making them refinery and development of such refinery technology, and then making it to your useful products. Under this consortium, various other companies have also joined in the name of Make in India program as well as Atmanirbhar Bharat. This race is not only on the earth. I mean to say that on the land. This race was extended up to below sea also, deep sea belt case also, especially for securing sulfide ecosystems as well as polymetallic nodules, of course dark oxygen. But major concern is cobalt-rich ferromanganese crust under the seabed, which could be formed as a layer of a solid underwater, which is I think nearly 5 to 6 kilometers deep in sea. So which could be appeared to be like this. So securing those what is cobalt-rich ferromagnet, which indicates that cobalt, iron, manganese, some other rare earth crust elements also can be possible to secure them. That's why deep sea mining is also become very serious race now. For example, in India periphery, you could see that the belt in this region, which has become the very strategic sea area. That's why the race on sea and the competition on the sea area, grabbing the sea area, has become very much important now, significant now. That's why many countries are trying to secure the sea land areas, out of which International Seabelt Authority (ISA) is started giving the license to various countries to go with underwater mining license. Right now, India has secured two what is called underwater and deep sea mining licenses, and another two were applied. In this also, China is in top race, who has secured 5, and also Russia secured 3 in the underwater mining licenses. And particularly, you could see that USA has shown no interest among it. Actually, it is not true. Actually, most of these companies who secured these licenses were actually under the lot of investment was made by USA itself. But coming to India and Japan, it was majorly concerned by the government itself. And Japan companies have made investment in India. For example, you could say that Suzuki, Toshiba, Denso. Okay, that means, okay, I'll change the order. What is called T for Toshiba, D for Denso, S for Suzuki, G for Gujarat. Okay, so this plant was placed in Gujarat. So they are aiming to develop 2 plants. One is with a large investment up to 50 billions actually. In that, okay, they are aiming to fabricate the what is called like supercharged lithium-ion battery systems. These supercharged lithium-ion battery systems majorly will go with the different dimensions, majorly go to Suzuki Automobile Company, because they are aiming to replace the conventional lead-acid battery systems in the car systems. They wanted to use the lithium-ion battery system. So majority of the fabricated batteries will go to Suzuki. That is the purpose of. That's why they have 50% of equity stake here, and it has produced. I mean, this company has also currently nearly 1,000 employees were already joined in this, and it has of course these companies have a lot of opportunity for young engineers and also material scientists too. And the technology they are developing is towards the roll-to-roll technology. That what is roll-to-roll technology? You could see that it could reduce the human interference. That means with less human efficiency, I mean, less human efforts, you could go for large scale production like this one. For example, the example shown here, and for the screen printing and for the battery coating technologies. So this has become one of the major challenge now, because the current battery systems are fabricated mostly under no vacuum condition. In the future, if you want to design such kind of advanced battery systems, vacuum technology is required. Why? Because, for example, if these batteries require lithium as a metal. That's why to coat lithium as metal, it requires the low vacuum condition and no moisture condition, for which, and it has to be adapted for the roll-to-roll technology. That's why they wanted to fabricate the lithium foil in the size of 10 micrometers thickness. They wanted to coat on a copper foil, and then they wanted to use it for battery technology. I am explaining this one. This is one of the challenge for one company's challenge, that is ULVAC company's challenge. Likewise, many companies actually are in the race, participating in the race, and they are trying to secure as many as patents to grab the market share, as I said. And you would also understand the battery nomenclature from its name itself. Okay, let's look at these various battery systems. They can be fabricated, they can be connected in series, parallel, and then the combination of it. And this battery system must require a battery management system to control the heat upon overcharge condition or long-term charging condition and all. And for example, if there is a label here which represents 6LF22, that means like 6 means 6 cells are connected in series. L means you could see the label nomenclature. This is alkaline type battery system. That means F means flat battery, and 22 means it's a size. So by looking at the nomenclature, you can clearly understand what is battery and what type of battery, what is its shape, what is the chemistry inside also, you can clearly understand. Let's go back to the basics of it. For example, in the case of lithium-ion battery, how would we understand its voltage, open circuit voltage, how to understand the capacity, or how to calculate the capacity. For example, if here you could see the standard redox potentials of various chemistries, various metal chemistries. For example, here you could see lithium nickel oxide, lithium cobalt oxide, lithium manganese oxide. These are the cathode candidates for lithium-ion battery system, which have the redox potentials in the positive order, and the anodes like lithium and graphite, these are the cathode systems, anode systems, and their redox potentials are in the negative side. That's why lithium cobalt oxide, although it is called as cathode, we should call it as positive electrode, because it shows the positive redox potential. Not only that, it is a source, and it is a it is a source of lithium during oxidation, which limits the capacity actually. For example, if I want to understand the open circuit voltage of this combination, for example, lithium cobalt oxide to lithium or graphite, for example, if you see lithium cobalt oxide redox potential is 0.9, and graphite redox potential is minus 2.9, which is equal to 3.8. That is cathode minus anode. 3.8 is the open circuit voltage of this combination. Whereas coming to calculation of theoretical capacity, it comes with the fundamentals called Faraday's laws of electrolysis. Faraday, how he introduced to electrolysis, that's a different story. But whatever it is, we can use that technology. I mean, for actually to know the battery capacity using this simple formula. That is theoretical capacity of the battery, which is of depends upon this oxidation reduction reaction. For example, complete lithium ion was lithium was participated in this electrochemical reaction. When X is equal to 1, what happens? This becomes 1. Faraday constant, it becomes 26.8015 ampere hour per mole, and molecular weight of the lithium cobalt oxide can become the theoretical capacity. It is around 273.8 milliampere hour per gram. But is it possible to achieve such a high theoretical capacity? Definitely not. The reason is, for example, this is a lithium cobalt oxide and its crystal structure. I don't want to give you much complexities. I'll try to make you very simple, to understand very simple. Lithium cobalt oxide X value start from 1:0. This is how intercalation, while in deintercalation, the stoichiometry of lithium can be decreased. So decrease means from 1 to it could be decreased up to 0. That means around 1, the structure it is composed of hexagonal layer structure having O3. O3 means 3 octahedral planes. 1, 2, 3. So 3 octahedral planes can be, which is having the lithium in between. So in between the layers. Whereas this O3 structure is stable up to 0.5. That means 50% of lithium ion exchange. Later, there is a sudden shift in the crystal structure from O3 to monoclinic structure, which becomes the lattice parameter. X value is C-axis. C-axis is nothing but height of the structure. A-axis is nothing but maybe the width of the structure. This structure height can be enhanced like this. In such a case, the structure can be totally collapsed. So the major limitation here is lithium ion exchange percentage, that is up to 50%, with which we can calculate using the theoretical formula. In place of 1, if you fill it with 0.5, you will get only 50% of its capacity, which is equivalent to 136.9 milliampere hour per gram. This is a practically achievable capacity from the lithium cobalt oxide. That means structure is the limit for getting the battery capacity. And let's talk about the battery influence of C rate. C rate, okay. During the oxidation reaction, when you apply the cathodic current, you will get a plot like voltage versus time like this in this plot, during which lithium ions can be deintercalated from lithium cobalt oxide to cathode. In the reduction process, when you are applying the ID curve, that means standard current, the discharge current, the curve appears to be like this. Okay, during which lithium ions again coming back to its interstitial sites. Later, during the charge difference between the time difference between charging, that is T of charging, that means charging time in hours, and the IC, that applied charging current, we can, and the load of the mass, I mean load, lithium cobalt oxide loaded mass, we can calculate the charging capacity. Likewise, we can calculate the discharge capacity too. What happens, when you increase the charging C rate is nothing but, it is a C rate nothing but, okay, for simplification, I can explain that C rate is a charging rate. That means in terms of time. For example, 1 C rate means the charging time is 1 hour, discharging time is 1 hour, it has been 0.5 means it becomes half. That means time is doubled. That means 2 hours of charging. In such a case, like the C rate, with the increase of C rate, the battery capacity, there is a decrease of battery capacity can be expected. I'll tell you why. The reason is very simple. When you plot this voltage and capacity plot, that voltage into capacity becomes the battery energy stored in the battery, which is a rectangle now. But actual curve seems to be like this. The difference in the area occupied in this curve and the expected region is the loss. That loss is majorly attributed to battery internal resistance and its ionic resistance too. Because of this, when you are giving short time for the mobility of high amount of lithium ions, what happens? They cannot participate completely in the reversible reaction. Then that leads to the loss of energy increases. That loss of energy can leads to heating of this resistive element which is inside the battery, which later decimates the energy in terms of thermal energy. So battery get hot. So like fabrication and commercialization of lithium-ion battery, you could see that these are the various steps of lithium-ion battery fabrication: mixing, coating, calendaring. Mixing is nothing but lithium cobalt oxide, for example, lithium cobalt oxide and conductive additive and a binder can be mixed approximately in this ratio, or it depends upon researcher to researcher. And this can be mixed by using some appropriate solvent by planetary mixing and make this as a slurry. This is a thick slurry, and that slurry can be coated on a current collector, and it could be rolled and calendared to densify the electrode and then stack into the shape and making them in an array. But there is cathode separated by anode, separated by membrane, and then anode, like that. It could be stacked into and it could be packaged, and later electrolyte can be filled, and there must be some aging time is required because this electrolyte has to be absorbed by the electrode materials, and all this process has to be done in the clean in-room environment, which is an additional cost of the battery system fabrication. And for example, the same thing, if you could have seen in the laboratory scale, you can also fabricate like this. Okay, for example, if you take for 3 grams of lithium cobalt oxide, these are the weight percent you could say, and then binder to solvent ratio is 1:15% you could take, and with this percentage you can calculate the battery in this order. For example, take first weighing them, mixing them, if possible try to stir them to make a good slurry, and then coat them on the electrode foil, dry them like this. You will get, after drying you will get like this, and then make it disc cutting to this shape. Later densify them using the calendaring machine, and then fabricate like this kind of battery. Okay, this is a 2032 battery. That means through its C means it's a indication of lithium-ion battery. R means it's a round in shape. 20 means its diameter. 32 means 3.2 millimeter thickness. So this is how we can understand that 2032 means, what it means. And later, so this battery can be tested. And calendaring, as I told you, the calendaring has its high influence because the prepared electrode initially, the particles, the cathode particles and conductive additive within the binder system, they are not well connected. Upon calendaring, they can be well connected. And then with the increase of this electrical connection and the densification, probably it can enhance the capacity too in this order. So these are the various as prepared sample here. And then calendared 5 megapascal, 10 megapascal, you could see that reduction in the thickness too. This is how the density of the battery can be enhanced. And one of the important thing is augmentation of controlling the aggregation state of the carbon particle, which is conductivity 2. This is a cathode particle, and these are the conductive carbon carbon black particles, ethylene black particles. If they were aggregated, not well connected, what happens? Electron cannot be transported to its intercelestial site, so that this lithium and electron cannot be recombined, so that the battery capacity can be decreased like this. But upon increase of carbon content, you could see that upon tuning this carbon network connection, probably we can enhance the battery capacity within less amount of inactive electrochemically inactive material. That means we can load more amount of cathode electrochemically active material, more amount of lithium cobalt oxide in the cell. So that's why we are aiming to what is called modify this network structure upon using the electrophoresis effect. And this concept was recently adopted for the special invited lecture at EC, that is Electrochemical Society Prime 2 2024 in USA. Which is, I think I'm going to attend this conference for presenting a special invited lecture here. Later, this is a simplified lithium-ion battery structure. This is a charging and discharging concept, but electrolyte can be decomposed upon high voltage condition as well as a high temperature response and long cycling. This electrolyte first reaction could be electrolyte first reacts with the metal component. That metal could be transformed to the fluorine in the electrolyte can react with the metal, which could form as a metal fluoride. And then upon oxidation reduction reactions, possibly that could lead to formation of lithium fluoride, lithium carboxyl group. Such kind of a layer can be formed. Such layer, and another case is on the this has becomes the irreversible lithium-ion exchange, through which lithium dendrite can propagate on the anode layer like this, probably, which leads to short circuit and then leads to the formation what is called burn. This liquid electrolyte catches this thermal runaway, probably leads to catch the fire. That's why these liquid electrolyte are currently believed to be it is unsafe. Slowly moving towards the solid state is very essential. So if you look at, we are using battery, the moving towards solid state can issues the high stability, scalable fabrication, high energy density for all our daily appliances, as well as these. If you look at the various solid electrolyte materials, these are oxide, these are the sulfides one, among which oxides, lithium tantalum phosphate is recently become one of the good cathode candidate, and LLGO, that means garnet structure, lithium lanthanum zirconium oxide, with assisting of dopants, probably it can issues the cubic phase stability, which can give the ionic conductivity in the order of 10⁻³ Siemens per centimeter, where sulfides can issue some more amount of high stability, high stable ionic conductivity. But that means false sulfides and oxides can be used as solid electrolytes for the all solid state battery development. The major purpose is, for example, when in the liquid systems, you could see that liquid can penetrate into the cathode electrodes, so that ionic conductivity around the particle can be assured. So, but in the case of solid state electrolytes, it could what is called give the interface grain boundary interface interface challenges, which leads to interfacial resistance. That means the resistance elements can be expected within the electrode elements as well as the electrode electrolyte interface within the electrolyte itself. So that is surface modification of this cathode becomes very important. So the people have proposed various metal oxides, various lithiated metal oxides. If it is metal oxide, it can assure the high lithium electronic conductivity, but lithium ion conductivity can be compromised. Whereas in the case of lithiated transition metal oxides, as a coating candidate, electron conductivity can be compromised. But what we proposed was, we need to have a strategy called heterogeneous nucleation of the cathode coating, ion conducting coating, as well as it should offer a carbon network. Along with the carbon decoration, we could expect the electrical conductivity as well as ionic conductivity, through which we can suppress the interface grain boundary interface resistance too. This is a strategy we are working on it. So likewise, this is the significance of nano coating for the particle for the development of all solid state batteries. Here we could see the various drying processes, such as which are majorly based on the principle called electrofusion, hybridizer, theta composer. So these are the various companies and the strategies they have used. Basically comes under these fundamental concepts. And there are wet coating processes too, but wet coating process majorly used for fluidized wet coating, which are majorly used for our medicinal application, tablet fabrication. For example, titania coated some medicine, medicine, such kind of thing can be done by the fluidized bed, which is existing technology. But problem with this technology is, their particle sizes requires very high amount, almost like 5 millimeters in size, and the least one is 35 microns. Such a high amount of coating thickness, it is not required for solid state battery development. Solid state battery requires a nanoscale coating. That's why we proposed a novel coating technique which is based on fundamental sol-gel processing, which is starting with metal alkoxide. So metal alkoxide is nothing but metal, and it is having the alkyl groups, okay, in this order. So these alkyl groups are connected with oxygen. R is alkyl group, O is oxygen. So metal alkoxide functional group it is. Thus that metal alkoxide, when it is added with water, what happens? Maybe it could be hydrolyzed. This is called hydrolysis reaction. Later, when the another hydrolyzed metal alkoxide was side by side, problem when it is dehydration reaction has occurred, which becomes metal oxy metal network can be formed. So this kind of polymerization or polycondensation can be expected. There is another sort of reaction called polycondensation reaction. When this hydrolyzed metal alkoxide can be reacted with what is non-hydrolyzed metal alkoxide, then ROH can be, that means polycondensation ROH can be removed, so that metal oxy metal network can be extruded. That means this metal oxy metal polymerization can be expected, which forms as a gel network. So basically we use the sol and gel reactions for the coating process. I'll tell you why and how. So we disperse these particles which are in the 10 micron in region. So this is a what is called metal alkoxide precursor we design. So such metal alkoxide precursor, when we disperse the particles inside by simple rotary evaporator, so this particle surface can be first hydrolyzed. That means it used to have hydroxyl group on the particle surface. When this is started reacting with metal alkoxide, then by dehydration reaction, which I explained previously, so it can make a bond like metal oxy metal network structure. Here also the same. It could also react with oxygen metal, oxy metal, such kind of metal network can be formed. That means first it makes chemical reaction. Later, upon increasing the concentration as well as temperature, when it reaches to saturation solubility curve to supersaturated solubility curve, its thickness can be enhanced. Upon certain point, because the coating material and this material have the same electrostatic zeta potential, so this becomes electrostatically repel, so that after certain constant, that means the thickness can be limited. You cannot go beyond that. So likewise, we can structure the heterogeneous nucleation to homogeneous nucleation condition. So we can control the thickness by changing the concentration and its deposition process by temperature as well as pH of its particles as well as the solution. This is a solution. For example, okay, do not make it complex. I'll try to make you very simple here. I use the metals lithium, tantalum, lanthanum, zirconium. So these are the metals from the periodic table I have taken, and this is a good electrolyte material. So I wanted to use this prepare this as this molecule in the precursor itself. To make this precursor molecule in the precursor, what I have chosen was the metal's electronegativity as a major concern. Metal electronegativity I considered here, and then through which, by using this simple formula, I can calculate the metal oxygen covalent bond strength. That means degree of ionicity can be calculated. Here you could see that zirconium oxide degree of ionicity is 67%, tantalum oxide 61%, and then 75%. This among which the reason this is the lowest was maintained, but tantalum oxide also was maintained. So we can choose either one of the alkoxide as a starting point. But tantalum here is a dopant. So that's why I have chosen zirconium as a starting point. This is a zirconium alkoxide molecular structure, and I chelated with acetic acid, through which I have created a steric hindrance. That means it blocks the not to participate in the hydrolysis reaction. Then OH cannot be attached here, so that the other side chains can be attached to the zirconium by polycondensation reactions and dehydration reactions. So likewise, zirconium oxide zirconium polymerization network can be expected. Later, to this carboxyl group, lithium can be reacted, so that lithium coordinated carboxyl group can be attached. And then upon addition of lanthanum, lanthanum can be reacted in this site, so that lanthanum oxy, zirconium oxy, lanthanum oxy, such kind of metal network can be formed. So they are in the shape of polyhedra. This set of oligomers can be prepared within the solution itself. So that molecule directly can be, this is a powder, when corresponding powders for calcined at high temperature, we get the pure phase within 650 degrees centigrade. For more details, you can go through this paper. And such kind of molecule, you could use it for what is called nickel, cobalt, manganese cathode particle surface. By increasing the coating concentration, you could see that coating thickness have been increased, a minute, which is in the order of nanoscale. You could see that the range is approximately that it is somewhere around 10 to 11 nanometer in thickness. Approximately it is 20 nanometer in thickness. For example, if the increase of coating concentration from 0 to 0.005 mole percent to 0.02, you could see the segregation of coating particles, which means this condition is not good. So uniformity is very important for the nano coating of precursor on the particle surface. That means we successfully prepared a nano coating on the particle surface using a simple sol-gel concepts. And it has its temperature dependency too. At low temperature, around 300 degrees centigrade, before evaporation of the carbon groups, you could see the lot of carbon. The surface was more decorated with some sort of. You could see the change in this no coating structure to coating structure. You could see a lot of carbon on the surface. Upon increasing the temperature up to 500 degrees centigrade, that density of decoration was decreased, and it leads to very less in coating. Thickness was decreased. You could see that the propagation of particles and the distribution of particles, where you could see the different colors, distribution. Here you could see that nano coating has been assured at 750 degrees centigrade. Most likely it seems to be the island kind of structure. So it gives the challenge how to estimate the coating structure. The coating structure, for example, if it is a island kind of structure, or fully decorated, fully coated structure, or a mixed kind of coated with island kind of structure, how to analyze that coating structure within the nanoscale range, which is distributed in the nanoscale range. So we adopted a simple technique called by using the XPS. XPS is nothing but extraphoto electron spectroscopy, which can analyze roughly, it is not accurate, it can roughly estimate the elemental composition on the surface, which is in the range of 2 to 12 nanometer in the range, whereas XRF can measure deeper into that. It is in the order of 10 microns. So that means, in summary, I can say that XRF can measure the whole elements, whatever that available within the particle, starting from the surface to core, whereas the XPS is mostly concerned with the coating element. If I plot the coating elements ratio along with the total element ratio, that element ratio can give the different spots. For example, when the XPS is XRF content is very high and XPS content is less, then it could be island kind of structure. When the XPS content, that means surface amount, is very high, whereas XRF content is less, that means it has the high amount of coating on the surface. So this is the strategy we adopted for estimation of the coating structure, and to analyze which coating structure is good for batteries, all solid state battery development. This is how we could see that. Whereas 8.5, that means a pH 8, and you could see that. Okay, I'm not going much details about it. When we maintain pH 8 condition for the precursor and coating elements at 5 milliliters per second, at that temperature, we could expect the high XPS content and less XRF content, so that it has the high homogeneity on the coating structure. Coating structure is highly homogeneous relatively, whereas X6.1, that means pH 6 and 1 milliliter per minute evaporation rate, which is having the relatively inhomogeneous coating structure. So, and remaining all are in between. Why the pH is so important? You know, zeta potential is one factor which is which is very good to understand such kind of coatings. Starting with our process, if you plot that pH variation along with the zeta potential, it's in simple. I can say that it has a positive and negative. If I see that precursor zeta potential as well as the precursor particles zeta potential and core particle zeta potential, the difference between the particle electrostatic potential is, that means at the condition pH 4 they can be attracted, at condition pH 8 they can be repelled, because both are in the negative side. So likewise we can understand at what pH condition, which pH condition this is more good, more not good. When such kind of electrostatic relation can be predicted for the precursor solution as well as the core elements, through which we can understand the coating structure and control the coating structure too. So this is how the battery we have fabricated. And if you look at this one, with the this is a graph which compares the structural factor as well as the electrochemical factor. In the structural factor, for example, 8,5 I said, right, which is having the highly homogeneous coating structure compared to all other metals, which is having the high capacity retention compared to low coating inhomogeneous coating structure, that is 6,1, which is as predicted by the XPS XRF relation. Not only that, at 1C rate condition also, this fully coated sample have shown the high stability. This is what I tested in the liquid systems. If you go with the solid systems, okay, I will explain the solid systems. I have chosen LLGO because of its better electrochemical potential stability, and this is how the all solid state battery can be fabricated. Okay, step 1, the solid electrolyte, sulfide based solid electrolyte can be densified at this megapascal. Step 2 is, and then after densification of the electrolyte, on the top of the electrolyte we can make the cathode mixed with the solid electrolyte in this ratio, 1:1 volume ratio, and make it as another layer, and then make it densify little higher than the electrolyte densified state. And later, other side of this one, indium tin lithium alloy was put, and which was densified. This sort of assembly was fabricated when bring it to the design cell, which is having a spring assistance, so that its electrochemical expansion, volume expansion can also be managed using such kind of cells. So this is the cell we fabricated. And I must tell the another one, which is the conventionally we will do the cell activation test for at low C rate for 3 cycles. Later, which to understand its durability, cell durability, that means after charging, we put the constant potential, we maintain the constant potential up to 120 hours at higher potential, that is 4.55 volts, which is not conventional. For comparison, 4.25 volts also we measured. So maintaining the same voltage after the discharge has been the cell was discharged at around 3.95 volts. We started estimating its impedance, because upon maintaining such a high voltage condition, what happens, cell can be expanded, the structure of the NCM can be expected to expand, so that the durability of the cell can be clearly understood using this simple floating test. And if you see that there are 3 different lithium niobate coated NCM, LLGTO coated NCM, heated at 350 degrees centigrade and 500 degrees centigrade. You could see that impedance was decreased compared to lithium niobate candidate, and you could see that capacity retention was maintained up to 350 degrees centigrade. I'm so sorry. Capacity retention was maintained up to 83% for the NCM coated at 300 degrees centigrade. When this cell voltage was increased up to 4.55 volts, this was drastically reduced to 69%. We need to understand why. The reason we estimated using SCM analysis as well as XPS as well as synchrotron radiation, out of which we understand that there is a probability of upon increasing from 300 degrees to 500 degrees centigrade temperature, there is a thermal driven interface which is majorly composed of lanthanum nickel oxide has been which is an inert layer, which is actually the reason for the increase of the cell impedance. When high cell impedance means it's a resistance, and resistance was increased so that its electrochemical behavior will drastically reduce. To control this one, we have adopted this strategy. What is that one is, we replace the LLGO with lithium zirconate, which is can maintain can promise the higher lithium chemical potential between the cathode and electrolyte, okay, compared to LLGO. But if you look at this fluorine can assure the wider potential window, starting from lithium ion cell voltage up to 1 volt to 6 volts or some. That means the fluorine doping can also be an effective strategy. That means fluorine doping, anion doping has assured the higher chemical potential window, so that the interface between, it could be a good interface between cathode and electrolyte, so that the battery retention rate can be improved. With this strategy, we succeeded to achieve the battery stability up to 92%. This is all solid state battery. Battery stability was achieved up to 92% with the lithium zirconate coated, and fluorine percentage up to 10%. And then I would like to show, you could see that high degree of homogeneity of the fluorine distribution and oxygen distribution. You could see that on the surface of zirconium. And we examined some other experiments too to understand the fluorine effect. And later we understand, okay. And sorry, it was holded. Anyway, in simply, I can say that amorphous material, which are good for the fabrication of amorphous coatings, are good for the all solid state battery stability. So you could consider, for the development of all solid state battery, a nanoscale of amorphous coating is highly important, and we could use this with which we succeeded to achieve 95.2% of capacity reduction for the all solid state battery. Currently, our technology is directly using for Toyota battery systems, and Toyota company directly adopted our technology for into their cell fabrication. Now it is under testing now. Yeah, with which I would like to conclude my talk, and thank you so much for giving this opportunity. I skipped majority of results, but I hope I have reached students with the fundamentals related to lithium ion battery. Thank you so much.
Thank you so much, Jeevan, sir. I would like to have some questions. Shall I,
Yeah, please.
sir?
Please,
Jeevan.
please.
Yeah. We have one questions from our HOD ma'am.
Yeah, please.
Congratulations, Jeevan sir. The talk is very excellent. And there is a question from my side. In spite of number of disadvantages of lithium, we are using lithium ion batteries widely, is it?
Yes.
Is there any battery that replaces lithium, sir?
Yeah, of course, yes, ma'am. No, maybe although it is still in the R&D sector, but sodium ion batteries, I'm believing to be can replace the lithium ion battery technology in near future. Not only that, battery systems also, yeah. Sodium ion batteries has its wide scope, I think. I'm believing that.
Okay.
I'm also working on sodium ion battery systems, so I can understand that clearly that it can compete lithium ion batteries in race.
Okay. Thank you, sir.
Thank you, Jeevan, sir. Shall I ask you another question?
Please, ma'am.
Okay. Which novel material will you suggest for our, solid state batteries? According to our latest technology. Novel batteries. Novel material for the solid state batteries.
The majority, okay. I'm working with two companies. One is Toyota as well as Mitsubishi. So Toyota company major concern is not materials. They are compromised with the existing materials. However, their major concern is the technology, the current technology, solid state technology is so expensive, they are aiming to make it as cheaper as possible. In such a case, their concern is development of highly efficient anodes, which can be adaptable for roll-to-roll technology. That is their major concern, for which what I am working is, the carbon black particles, which are in finer size, those carbon particles surface can be, now we are nano coating on the carbon particles, which are in the range of 40 nanometer in the scale. The particle itself 40 nanometers, we wanted to control the coating thickness. That is one consideration Toyota is concerned. Whereas Mitsubishi is majorly focusing on solid alkylate candidates, not in the cathodes or anode systems. So the solid alkylates, they are now switching to oxide-based solid alkylates, which are lithium tantalum phosphate. That is the major concern, which can assure the ionic conductivity in the room temperature up to 10⁻³ Siemens per centimeter. So likewise, each and every company has its own goals. So I can say that we cannot particularly assign one material which can be in the race. So that is what my answer.
Okay, thank you, sir. Sir, one more question from our attendees. Some Akshaya, I think she raised a hand. So I request Akshaya to unmute your mic and you can ask your doubts. Akshaya. I request all the attendees who have any doubts regarding this topic can raise your hand and you can unmute your mics. You can ask. Okay. Shall I move to the next session?
I'm sorry,
Usha,
during my presentation, is it audible, everything?
Yeah, it's very clear. It's very clear, no doubt.
Actually,
So, Dr.
my
Usha
presentation
Pravina.
is stuck
Yes,
in the
sir.
jury.
Sir, I have a doubt, like, I don't know whether it is a myth or really we keep hearing about the things that these electrical vehicles, when they are used with ionic batteries, we need to worry about the safety, because they usually say, and we have seen one or two incidents saying that when it is kept on charging, there is a chance of the vehicle affected with fire or something like that. So can you please throw some light upon this particular thing, sir?
Yeah, battery. So electrical vehicle damage means it met with an accident majorly due to battery, in the sense. Here, two major concerns actually important. One is the battery chemistry should be modified. Secondly, the software related to battery operation should be modified. I can say that battery management system needs to have more secured. That means, like, even in the liquid battery systems, they can operate up to 4.3 volts safely as long as they can. But when the temperature and long time charging has been influenced, the battery system, it catches the heat, so that heat can be what is called flame. It start flames. That liquid electrolyte can catch that heat and then it blasts. Okay, so that means such kind of thermal fluctuation has to have maintained by the circuit, that is called battery management system, that has to be maintained. Some companies actually working on it. Now they have produced very high-end BMS circuit so that it cannot catch any fire. Okay, that is second thing is battery chemistry. Battery chemistry now with the solid state system. Okay, I'll tell you, my battery, even if you directly fire at 120 degrees centigrade also, my battery cannot catch any fire. Likewise, such kind of technology is now already existed. Now it is under testing. So I can say that with solid state systems, with solid state battery systems, probably thermal runaway cannot be possible, so that we can expect more safer electrical vehicle systems within 2 years for sure.
Okay. Thank you so much, sir. And the talk was really wonderful, sir. Very, very informative.
Thank you so much, ma'am. Thank you so much.
Thank you, Jeevan, sir. One more question from Mahendra. Mahendra.
Good afternoon.
Mahendra.
I hope
Yes.
you hear.
Yes, I
Yeah.
can.
Yes, sir.
Good afternoon, sir, for you, and good morning for everyone. So, my major question was like, what is your major or minor motive of this work, or like working on the battery? I mean, the energy storage system.
From my PhD till date, I am working in the same research field because that much I love this energy storage systems field. From my in the during my PhD, as Sandhya ma'am introduced me, I'm working. I learned some basic from Muhammad Hussain sir. Actually, he himself gave me a free hand to learn many things. So I was by the time we had an opportunity to continue in a major research project sponsored by DRDO. Under that project, I'm lucky to go to ISC and spend my time over there. So that I started and learning about electrochemistry. When I started learning about electrochemistry and then I correlated the thin films, I believe that thin film batteries may not be successful. That's why I wanted to understand the material science, how a material can be fabricated. I don't know anything. Even after completion of my PhD also, I'm not introduced to material science, how a material can be fabricated using with solid state technology also or liquid technology. I was not known. I mean, so I spent a quality time or around 5 years. I have produced only 2 or 3 papers only in that 5 years. But I majorly concentrated to understand what is that material science, how I can design my own material. That is my major challenge. So that's why I choose to come to Japan. Luckily, in a material science group. So I started learning from students also. Sometimes I started learning from professors. This is all your interest, your interest. That is why I believe that material storage, I mean, energy storage itself has a lot of opportunities. When opportunity is there, materials challenges are there. When material challenges are there, material scientist is required. So I learned. Now I am effectively using my knowledge for the benefit of developing such advanced technologies related to energy storage systems.
Yeah, thanks for your clear answers, sir.
Thank you so much.
Sir, is there any questions from our audience side? Otherwise, I will move on to the next session, scientific sessions.
Yeah, if anybody have any doubts, you can mail me. I think you can get the email ID from the organizers. You can mail me at any moment. Thank you so much. Thank you so much for everyone, especially Jayasree ma'am. Thank you so much.
Thank you, Jeevan sir. And next, we want to start the scientific sessions. Before that, the scientific sessions are now chaired by the chairperson, Dr. Jeevan Karunateja Madam, Osaka University, Japan. So I would like to invite our J. Radhakrishna sir, our department faculty, to introduce her. So I'll hand over this to Radhakrishna.
It's my child.
Good afternoon, everyone. Today, I am really glad and feel proud to introduce our special invitee, the young and dynamic lady, Dr. Jeevan Tarunateja Garu. She has dedicated her career to finding innovative solutions for a greenery and more sustainable future. She is a postdoctoral fellow and specially appointed researcher by the Toyo Aluminum Research Lab of Semiconductors, Graduate School of Engineering, Osaka University of Japan. She worked as the software developer, GVSR mapping technologies, research assistant, and postdoctoral fellow in Nano Devices Lab, Inorganic Laboratories, Kitami Institute of Technology, University of Japan. She is an engineering graduate in electronics and communication from Acharya Nagarjuna University, India, and got her master's ME from the University of Japan. She has published nearly 30 peer-reviewed research journals and international proceedings. The Electrochemical Society of Japan, in their 85th Electrochemical Conference, has awarded her the Best Presenter Award in 2018. It's really great, ma'am. It's not just her professional achievements that make her special. She is a passionate researcher for educating the next generation of women. Ma'am, really, we are lucky to have you here. Today, Dr. Tarun Teja Garu will share her insight on silicon multi-junctional technologies for next generation solar cells. Thank you, ma'am.
Dr. Tarun Teja, madam, please join the early. And unmute yourself, ma'am, please.
Okay. I hope I am audible now.
Yeah, you are clearly audible.
And my screen is also visible. How about my screen presentation slide? Is
Yes,
visible?
it visible clearly.
Yeah. Okay. Thank you very much for introducing me. And first of all, I'm very much thankful for inviting me to speak at this one-day international webinar on renewable energy sources and applications. And I especially want to express my gratitude to Jayashree Madam for making this opportunity possible. And I'm pleased to talk about on-silicon multi-junction technology for next-generation solar cells. Before we get into the topic, I would like to briefly share my background and the experiences that have led me to this field. And you already heard from the previously before introducer about myself, but I would like to share some more information about my education and work history. I began my career in India as a software developer before relocating to Japan with my family. There, I was inspired by the opportunities available, like the program through Asian Bridge program at Shizuoka University, which allowed me to pursue master's degree with the support of free exemptions and also scholarships. And after I continued my PhD in the same university, and also during my PhD, I worked as a research assistant in the Shizuoka University of Japan. After completing my PhD, I joined the Kitami Institute of Technology as a research assistant, where I gained some experience in material science research methodologies. Currently, I am working as a specially appointed researcher at Osaka University, specializing in the development of 3-5 solar cells and focusing on the solutions to enhance the solar energy efficiency. I would like to introduce the joint research system that I am working now. And this is like involving the Toyo Aluminum Company and also Osaka University, where I am currently working at the Toyo Aluminum Research Lab for Semiconductors. And this work is a part of a NEDO project, NEDO Research Funding Project, which aims to develop next generation solar cells. And this project is a collaboration between the company, Osaka University, and also the ACE Research Center in Japan, and also in collaboration with Nagoya University. The main goal is to the main goal of this project and this team is to develop the innovative technologies, especially the after beyond 2040, like in promoting the industry and academia collaboration. Let me introduce the company about Toyo Aluminum, where I am working. And it's a leading company in the materials and technology sector, known for its innovative products, as some of the products are mentioned here, like lightweight solar module. And this is the recent innovative product which was developed by Toyo Aluminum, and crystalline silicon solar cells. And we also make the silver paste and also the interference of aluminum effect pigments, and also some foil based projects and functional inks, these kind of products. Like this shows that how the Toyo Aluminum is shaping the future with cutting edge technology solutions and also these advanced technologies. I will start my presentation with this outline, and I will give some of the background about the current situation of photovoltaic energy and multi-junction solar cells and the alternative materials.
With the rising demand, particularly from electric vehicles, global energy are expected to grow significantly by 2050. Over the past decade, the solar photovoltaic installation have been increased dramatically and expected to reach the generating capacity of 500 gigawatts. And this growth shows that the solar energy is becoming a key part of our global energy strategy. Let's see why advancing solar energy technology is so crucial. And the first one is reducing the greenhouse gas emissions is essential for combating the climate change. And the second one is the cost of solar cell technology is steadily decreasing and making it more accessible. And the third one is the demand for electricity is increasing, particularly with the rise of electric vehicles. So that the solar power offers the clean and efficient solution to these challenges, and it is important for meeting our future energy needs. And we'll see the different types of solar cells focusing on their materials, efficiencies, and challenges. And these solar cells, first one is silicon solar cells, which are come in two different types, crystalline and amorphous. Over 95% of the market is uh, made with crystalline silicon solar cells, because they are popular because of their high efficiency, which is greater than 25%, and they also come with low cost. And the next one is like 3-5 perovskite solar cells, the main one, and also the 3-5 solar cells. However, they come with high efficiency greater than 30%. But the problem is with this compound semiconductors is high cost. So among these different types of solar cells, 3-5 solar cells are particularly promising due to their high efficiency, and which is often offer 30%, and also used in various applications like the vehicles made with 3-5 solar cells by Toyota, and also they are used with they are becoming critical for extending driving range and reducing the need for the frequent recharging, especially in these Tesla trucks. And they are also used in concentrator photovoltaic systems, which offer low generation costs while maximizing the energy capture. And these examples shows how 3-5 solar cells can drive the adoption of solar energy in new and innovative ways. Now let's see the structure and advantage of these 3-5 solar cells. These type of solar cells are come with stacking the different kind of materials with different band gaps as shown here, and allowing them to absorb the broad range of solar spectrum. And this method is illustrated by this absorption wavelength diagram, which increases the efficiency by capturing the more sunlight compared to these traditional solar cells. However, achieving this high efficiency is which requires selecting materials which is compatible with this lattice constants to prevent the defects. Despite their high efficiency, that is more than 30%, the 3-5 solar cells face challenges with this high cost. Materials such as, especially when we are using germanium and gallium arsenide substrates, they become more expensive, and the germanium wafer itself alone cost production cost of 50%. Additionally, and also directly stacking these materials with different band gaps gives more lattice mismatches with this wafer. So to address these issues, adding the silicon germanium layer to help the bridge between lattice mismatch with the silicon substrates, making the integration more feasible. And researchers are also actively exploring cost reduction methods for 3-5 solar cells to overcome remaining challenges and make these high efficiency solar cells more commonly viable. And next, this slide details how we create the silicon germanium layer using aluminum germanium paste. which is the aluminum germanium paste applied to this silicon substrate. And first we coat the silicon substrate with this aluminum germanium paste, and by heating the sample, the aluminum melts and reacts with the silicon wafer, the surface of the silicon wafer, and resulting in aluminum silicon germanium liquid phase. This liquid phase promotes through the mixing of the materials, and as the mixture cools, it solidifies into the silicon germanium layer on the silicon wafer. And this technique is efficient and more cost effective, making it is suitable for large scale production and also advancing the development of cutting edge solar cells. And this is the experiment process, that is paste making, screen printing, annealing, and evaluation. I would like to show quickly some of my results, that is some EDX mapping results. Here shown the silicon germanium layer found, we can see from the SEM results. And also we also measure the germanium concentration in the silicon germanium layer. And later we measure, we do the analysis of the crystal orientation of the silicon germanium layer. We confirm that it is matched with the silicon wafer. And also we do the polishing to see the smooth surface. As shown here, we remove this paste and we make this silicon germanium layer smooth. It looks like a mirror. And we also confirm that whether it really works as a PN junction diode. And also we use the silicon germanium buffer layers in the low cost silicon germanium diodes, waveguides, and also we are using the silicon germanium layer. This is the main part of our research. We use the ACE Research Center to do this high efficient technology like MOCVD and HVPV. We deposit the solar cells on our silicon germanium substrates. And next, in the last, before I conclude, I would like to share some information for those who are interested in studying abroad. That is called Asian Bridge program, where I also studied my master's and PhD. And this program offers full tuition fee and admission fee exemptions, and making it good opportunity for the international students. And there are also various scholarships like MEC scholarship, which covers full tuition fee and living expenses. And you can also apply the scholarship like JASO and local government and privately funded scholarships. Here in Japan, it is more common scholarships for the student. After your education, you can also find various job opportunities in academic positions and also various companies in Japan, as Japan is a hub of automobile industry. And if you are interested in applying this program, you can find more information in this university website. It's not only in the Shizuoka University, you can find various graduate programs by checking directly the university websites, and you can find the professor details, and you can find the scholarships, everything in the university website. So you can go through it and directly contact professors, as the email IDs are provided in the university website directly itself. And in conclusion, the use of screen printing and annealing to create the silicon germanium layers offers the cost-effective and scalable approach. Furtherly, we grow 3-5 materials with the silicon germanium layers. And this continued research and development are crucial for optimizing the performance and reducing the cost for the future 3-5 solar cells. And that's all about my talk. Then we'll continue the next sessions presentation. Thank you very much.
I invited all the paper presentees should take minimum of 3 minutes time each one. I invited first Dr. Umarani Madam, Professor, Department of Psychology.
Madam, please unmute yourself, ma'am. Kumar and madam, are you on the line? I request the attendees who are going to present the papers, please just raise your hand so that will be easy to call you.
I invited Dr. Bharati Madam.
Madam. Madam, shall I continue? Jayashree Madam. Jayashree Madam.
Yes, yes, madam. Should I go ahead with my presentation? Madam, you're not audible. You're not audible.
One
You're
minute,
not
1 minute.
Yeah.
Madam, please go on.
Okay. Thank you. Thank you very much. Well, good afternoon, everybody. Myself, Dr. K. Umarani, and I'm faculty of psychology in SPW degree and PG college. And as a behavioral scientist, my concern is more about with the behavior of an individual for the pro-environment. How we can make these changes in the behavior of an individual so that they go for this more of the renewable energy transactions. The main cause behind global warming and climate change is the overuse of dirty energy resources such as coal, oil, and gas. And that too by the nations to support the process of industrialization, urbanization, trade, and other economic activities. Now here, generating renewable and alternate energy resources is considered the most vital approach to controlling the environmental damage by controlling the carbon emissions. This is a basic thing we all understand that. Renewable energy sources are considered sustainable because they continuously grow with the utilization. The energy obtained from solar, tidal, wind, and biomass is renewable energy and is cost effective and never ending. In addition, these sources are environment friendly and help achieve better environmental quality. Increasing the role of renewable energy in the economy also lets the economy proliferate without damaging the environment. Proficient monitoring and energy demand are the factors that can determine the consumer's education and environmental mindfulness. Here comes into the picture the title of my paper, that is pro environmental behavior, role of ICT in the development of renewable energy transition. Lack of technology is considered an important hurdle in implementing renewable energy technology, especially in helping less developing countries overcome technical constraints which may promote environmental quality and green growth. Here, people have habits have from offline business to online business owing to the rise of ICTs. This may provide a new opportunity for the RE growth. Now here we can see, which we can see through these webinars. If it was not virtual, we all would have to go somewhere and enter the muscle to cut that carbon emissions. Generation of green growth, ICT can play a significant role mainly when you are easily available. Moreover, increased ICT can help store the electricity generated with the help of ICT could prove vital in overcoming the technological shortages.
Thank you, madam. I invite next participant is Deepak Kumar Behra, Assistant Professor. Sir, are you online? Deepak Kumar Behra.
Sir, please, if you are there, please raise your hand, sir. Okay, we'll go to the next participant.
Next participant is Dr. G. Salemma, Assistant Professor.
Good morning, madam. Good morning, madam.
Okay, madam. Present your paper, madam.
Ma'am, my topic is solar thermal energy for a sustainable future. My name is Sailama, Assistant Professor, Department of Publications, Roden University, Kuppam. The most promising renewable energy resource is solar thermal energy. The solar radiation is converted into heat that either can be used directly or can be transformed into electricity. Solar thermal energy is like geometrical, geothermal energy and heat pumps in the building industry. Solar thermal energy can be utilized for domestic water heating, drying process. Solar thermal energy has a wide range of domestic and industrial applications such as solar thermal electricity, solar space heating, solar desalination, solar industrial air heating, solar water heating, solar cooling, etc. So there is vast scope of solar thermal energy in domestic and commercial aspects. The present paper attempts to briefly outline the significance of solar thermal energy in sustainable developments. Thanks giving me this opportunity of the dais on the dais, ma'am, and organizers also. Thank you, ma'am. Thank you so much, ma'am.
I invite Dr. P.R. Bharati. Madam, Bharati ma'am.
Okay, madam.
Bharati.
Can I go ahead, madam? Yes, madam, I am in online.
Start your talk.
Okay. Okay. A very good morning to all of you. A very good morning to all of you. And my topic is, and first of all, myself, P.R. Bharati from Computer Science Department, SPG, SPW Degree and PG College.
Excuse me.
And my topic is
Excuse
advancements
me,
and...
madam. Please, Bharati madam, check. Hello?
Yes, madam. I am unmuted, madam. Is it audible, ma'am?
Your voice is not clear, madam. Please check the network. Some disturbances are
Yes, madam, it is.
intervening.
Oh, but I am connected. Now, is it okay,
Now
ma'am?
you're okay. Please go ahead.
Okay.
Video on.
Topic
Madam, please
is
on your video, ma'am.
Yes, madam. Just I have on, ma'am. Just I have Okay, ma'am. Shall I go ahead? Shall I go ahead, madam?
Madam, please go ahead.
Okay, madam. My topic is advancements and challenges in solar cell technology. First of all, see, in this topic, first of all, we must know the renewable energy. Renewable energy means energy from a source that is not depleted when used, such as wind or solar power. And coming to the solar cells are also known as photovoltaic cells that are devices that convert sunlight directly into electricity through the photovoltaic effect. This technology has garnered significant attention in recent decades due to its potential to provide a sustainable and environmentally friendly energy source. The operation of solar cells is based on the ability of certain materials, such as semiconductors, which absorb photons of light and release electrons and creates an electric current. The comprehension of the PN junction solar cell will give us hints to improve solar cells regarding efficiency, manufacturing cost, consuming energy for the fabrication. Silicon solar cells are classified into three types. First one is monocrystalline, second one is polycrystalline, and finally amorphous. Monocrystalline silicon cells are known for their highest efficiency and longevity, whereas polycrystalline silicon cells offer a cost-effective alternative, and finally, amorphous silicon cells, although less efficient, but flexible and lightweight. Solar cells provide more energy than other conventional sources, such as additional advantage of being lightweight and cost-effective. Developing cheaper alternatives to solar cells, such as amorphous silicon and polycrystalline silicon, are also in the pipeline. Current research reveals that in order to increase the amount of sunlight effectively used and focusing it, and layers of different materials could also be used. Recent advancements in solar cell technology have focused on improving efficiency, reducing costs, and enhancing the versatility of solar cells. Emerging technologies such as thin film solar cells, organic photovoltaics, and perovskite. That is, it is type of material that contains calcium, titanium, and oxygen solar cells have shown promise in achieving higher efficiencies and broader applicability. Thin film solar cells, which include cadmium telluride and copper, indium, gallium selenide, which is also known as CIGS, are lighter and less expensive to produce traditional silicon cells. Organic photovoltaics made from carbon-based materials are notable for their flexibility and potential for low cost. Perovskite solar cells, a relatively new development, have rapidly achieved high efficiencies with other materials to maximize energy conversion. In addition to these material innovations, research in solar cell technology also focuses on improving the integration of solar cells into various environments such as building integrated photovoltaics, that is BIPV, which allows solar cells to be incorporated into the fabric of buildings. Furthermore, the development of transparent solar cells could revolutionize energy regeneration by enabling windows and other transparent surfaces to generate the electricity. The efficiency of solar cells, often measured by the percentage of sunlight they can convert into usable electricity. It is a crucial factor in their widespread adoption. While laboratory efficiency have reached over 25% for silicon cells and over 30% for multi-junction cells, real-world efficiencies are typically lower due to factors like shading, temperature, and dirt accumulation. Despite the impressive progress, challenges remain in making solar cells are more efficient, affordable, and durable. The environmental impact of manufacturing and disposing of solar cells is a concern, particularly with materials like cadmium and lead used in some thin film technologies. In conclusion, solar cells represent a vital component of the global transition to renewable energy. With continuous advancements in materials, efficiency, and integration techniques, solar cells are poised to play a significant role in meeting the world's growing energy demands while reducing greenhouse gas emissions, etc. The future of solar energy is promising, but it will depend on sustained innovation and commitment to overcome the remaining technological and economical hurdles. Thank you, madam, for giving me this opportunity. Thank you once again.
Thank you, ma'am. I invite the next participant is Dr. G. Nagamani, Lecturer, Department of Hope Science. Madam, are you online? Nagamani, madam?
Yes, madam. Yes, madam, I am online. Good afternoon,
Madam,
everyone.
One humble request for all the paper presenters that please make your paper presentation limit to your 3 minutes talk.
Today, I am going to present a topic is on energy saving programs in developing countries. And I want to share screen.
Nagamani, madam.
Yes, madam.
Please continue.
Continue, ma'am.
Yes, madam. Energy saving programs in developing countries is my topic. I am Nagamani, Dr. Nagamani, Home Science Department, SPW Degree College. And today I am going to present the topic is on energy saving programs in developing countries. And the main energy consumption in developing countries is rising due to rapid industrialization, urbanization, and population growth. However, these nations often face significant energy supply constraints and environmental challenges. Many developing countries are implementing energy saving programs to address these issues, aiming to improve energy efficiency, reduce environmental impact, and promote sustainable development. Energy saving initiatives in developing countries typically focus on enhancing energy efficiency across various sectors, including residential, commercial, and industrial. Some of the key strategies include the adoption of energy efficient appliances, building codes, and lighting technologies are some of the strategies. Programs often incorporate incentives for retrofitting buildings, upgrading infrastructure, and promoting the use of renewable energy sources. Some of the initiatives like to replace incandescent bulbs with compact fluorescent or LED lighting can significantly lower electricity consumption. Government policies and international support play crucial roles in these programs. Governments may establish regulations and standards to promote energy efficiency, while international organizations and non-government organizations often provide technical and financial assistance. Some of the examples like Global Environmental Facility and the United Nations Development Program, which support energy efficiency projects through funding and capacity building efforts. Challenges faced by developing countries in implementing these programs include limited financial resources, inadequate infrastructure, and lack of technical expertise. Despite these obstacles, several success stories highlight the potential for positive outcomes. For instance, India's Perform, Achieve and Trade scheme has successfully incentivized industrial energy efficiency improvements. Similarly, Kenya's investment in solar energy system has provided off-grid communities with reliable and clean energy access. Effective energy saving programs in developing countries often require a multifaceted approach, combining policy frameworks, financial mechanisms, and public awareness campaigns. Tailoring programs to local contexts involving stakeholders at all levels and ensuring long-term sustainability are crucial for maximizing the impact of energy efficiency efforts. For conclusion, I can conclude that while energy saving programs in developing countries face several challenges, they also offer significant opportunities for reducing energy consumption, lowering greenhouse gas emissions, and fostering sustainable development. Continued support and innovation in this area are essential for addressing the energy needs of developing nations while mitigating environmental impacts and enhancing quality of life. Thank you, madam, for giving me this opportunity.
Thank you, madam. Next participant is Dr. Padma Srilata, lecturer in zoology.
A very good morning to one and all. Today, I'm going to present a paper on harnessing the sun, a review article on the implementation of solar energy technologies in agriculture and greenhouses. Myself, I am Dr. Padmasree Lata, lecturer in zoology, Sri Padmavati Women's Degree College. This article presents the importance of solar energy in agriculture. In some of India, solar is very high, which is as it falls on the ground. According to the literature cited, it is known that if 1% of the received solar radiation can be converted to energy, then this energy can meet the energy crisis of future world. Solar power, a renewable energy source that harnesses the sun's energy to provide heat and electricity. Solar energy has an extremely low carbon emissions and does not produce any greenhouse gas emissions. Solar greenhouse performs a latest innovation and necessity. Solar panels on the greenhouse structures capture sunlight, converting it into electricity. As we all know, the solar energy is most important in agriculture. Solar energy are growing in popularity or as follows that most of the agriculture field farmers can use solar powered agriculture, solar powered irrigation systems, solar dryers, solar movers, solar tractors, solar electrical fences, and solar sprayers. Here are some presentations regarding so this is the solar powered agriculture. So this is this is the slide which shows how the solar panels are very useful in the agriculture. So which reduces the fossil fuels, lowering their carbon emissions, lessen the soil erosion, prevent water, and cost saving. Solar powered irrigation system. It is a good sustainable technology. Farmers can place solar powered pumps that use renewable energy for irrigation crops rather than using diesel powered pumps that use fossil fuels. Here are solar dryers. Most of the farmers use dehydrators to dry their crops after harvesting. So if they go for solar dryers, it is very good cost effective and eco-friendly or environmental friendly dryers which the farmers can use to dry their fruits, vegetables, and grains, reducing the risk of the spoilages. Solar movers. These are another very good environmentally friendly and convenient machine, which is gradually or generally used in the lawns to cut the grass. And this is a solar tractor. This is a very good, attractive for farmers and environmentally friendly, which harnesses the power of the sun, perform the duties, reducing their carbon footprints. The solar tractors they are fixed with the solar panels on the roof or the top of the tractor, which includes motor, lighting, and other accessories which run through the solar panels. Solar electric fences. This is also most useful for farmers, but that in a way that the farmers, the animals, they ruin the vegetation. So the farmers can protect their crops from cows, elephants, buffaloes, etc. like this. If they used this kind of solar fences, which is eco-friendly and environmentally friendly, the farmers can protect their fields from animals. And this is another one is solar sprayers. This is also a very good equipment or accessory which is used in the agriculture applications to protect their field or the crop from diseases. And they can go for disease control, weed management, and fertilization. These solar, the barrel will be fixed with a solar panel which runs with a button. I conclude today's presentation that solar powered greenhouses give more profit to farmers with its lower energy costs, increased crop yields, and minimal environmental effects. These technologies can reduce dependence on fossil fuels. Solar-powered greenhouses are a preferred choices for sustainable cultivation because of their advantages. Solar technologies such as solar greenhouses, solar tractors, solar movers, solar sprayers, and solar dryers, and agriculture solar pumps offer a sustainable and eco-friendly, environment-friendly solution to meet the growing energy needs for the agriculture sector. I thank one and all the organizers for giving me this beautiful opportunity. Thank you.
Thank you, Srilata. The next participant is Sai Kumar Arla, Department of Physics, Egnam University. Sir, are you online? Sai Kumar Arla. The next I repeated, the next participant is Sai Kumar Arla, Department of Physics, Egnam University. Second name, Mohammad Musab. Jiangsu Kaima. The next one is and Shangwood Joe. Anyone are online? I am going to the next participant, Dr. K. Kusumalata, Department of Physics, Padmavati. Dr. V. Lakshmi Devi. Sorry, Dr. V. Lakshmi Devi, lecturer in electronics. Dr. V. Lakshmi Devi, lecturer in electronics. Lakshmi, are you online? I am going to the next participant. K. Kusumalata, Department of Physics, Padmavati Women's University. The next name is Pranita Muniratna. Anyone is online? I repeated the participant. K. Kusumalata, are you online? K. Kusumalata from Padmavati Women's University. I am going to the next participant, YB Kishore Kumar, Mohan Babu University. Sir, are you online? YB Kishore Kumar. Sir.
Ma'am, some technical issues there, madam.
Okay.
And are you not willing, sir?
Ma'am, some technical issues there. I will join with you in a couple of minutes, ma'am.
Okay, sir. Thank you, sir. I am going to the next participant, G. Saujanya, Department of Physics, Padmavati University. G. Saujanya, Department of Physics, Padmavati Women's University. Next name is Priya Sahini, G. Vinod, Lakshman Nayak. Anyone is online? I repeated the name. G. Saujanya, Department of Physics, Sri Padmavati Women's University. Madam, are you online? I am going to the next participant, V. Madhu Mohan. Mohan Babu University. V. Madhu Mohan, Mohan Babu University. Are you online, sir? Madhu Mohan, sir? Mohan Babu University, Madhu Mohan. Sir, Madhu Mohan, sir, are you online? Next. I invited next participant is N. Triveni, student of political science. N. Triveni. N. Triveni, student of political science. Are you online, ma? Triveni? You unmute and participate, ma.
Okay, ma'am. Respected madams and sirs, I wish a warm good afternoon to everyone. First, I would like to introduce myself. This is N. Triveni, who is studying in Sri Padmavati Women's Degree and PG College from 2nd BA Political Science Honors. Today, I am going to speak about renewable energy, a natural environment of developing countries. I choose this topic because I believe that renewable energy is a crucial component in achieving sustainable development, particularly in developing countries. As the world grapples with climate change, energy poverty, and economic inequality, renewable energy offers a solution that can address these challenges simultaneously. I am passionate about exploring how renewable energy can be harnessed to create a more equitable and sustainable future for all. And I believe that developing countries have a unique opportunity to lead the way in this transition. All we all know, energy is backbone of any economy. I believe that renewable energy is the key to unlocking a sustainable future of developing countries. The importance of renewable energy is crucial for developing countries because it offers a clean, reliable, and and hello, ma'am. Hello, ma'am. Am I audible?
Continue, Triveni.
Hello. Okay, ma'am.
Clearly
Despite the
audible.
benefits,
You are in clear audible. Continue.
okay, ma'am. Despite the benefits, there are challenges to adopting renewable energy in developing countries. This include high upfront costs, lack of infrastructure, and limited access to financing. Additionally, policy and regulatory frameworks may not be supportive, and there may be a lack of public awareness and education. In conclusion, renewable energy is a vital component of sustainable development in developing countries. While there are challenges to adoption, I believe that with the right policies, investments, and international cooperation, we can overcome these barriers and create a cleaner, greener future for all. So my suggestions are firstly, governments and international organizations must prioritize investments in renewable energy infrastructure. Secondly, we need to develop supportive policies and regulatory frameworks. Thirdly, we must raise public awareness and education about the benefits of renewable energy. Finally, I would like to extend my sincere thanks to my HOD ma'am, Sai Kumar madam, and Dr. K. Vijay Kumari madam. Their encouragement and support, their guidance has been invaluable, and I appreciate them believing in me. I am also grateful to Physics Webinar for this opportunity to present my ideas on renewable energy. Thank you for your support and for promoting me sustainable initiative, ma'am. Thank you.
Thank you, Vaishnavi. Thank you. I request all the participants, please, should maintain 2 minutes only. I invite the next participant is A. Vaishnavi, Department of Political Science.
Yes, ma'am. I'm present, ma'am.
Ma, unmute and you on your video, ma.
Okay, ma'am. Ma'am, am I audible?
Yes, ma'am.
Okay. Good afternoon,
You
everyone.
start your task.
Okay, ma'am. Good afternoon, everyone. Respected teachers, sirs, and everyone. I am A. Vaishnavi, studying in 2nd BA Political Science in Sri Padmavati Women's Degree and PG College. I chose the topic renewable energy versus fossil fuel energy. As we face climate change and energy challenges, it's crucial to understand the differences between these two energy sources. First, fossil fuel energy. Fossil fuels are coal, oil, and gas, and we have been using them as our primary energy source for centuries. However, they are finite resources contributing to climate change, air pollution, and water contamination. Second, renewable energy. Renewable energy sources are solar, wind, hydro, geothermal, and bioenergy. These resources are sustainable, abundant, and clean. They reduce greenhouse gas emissions, promote energy independence, and create jobs. So, if we compare between these two energies, fossil fuels are finite, polluting, and clean, whereas the renewable energy is sustainable, clean, and increasingly cost competitive. Renewable energy offers numerous benefits. It mitigates climate change, improves air and water quality, enhances energy source security, and supports economic growth. In conclusion, renewable energy is the future. It's time to transition away from the fossil fuels and embrace sustainable energy sources. With this, I would like to end my presentation by thanking everyone who have supported me, especially my mentor, Dr. K. Vijay Kumari Madam, for giving me this opportunity to participate in this physics international webinar. Thank you.
Okay, thank you, ma. Thank you, Vaishnavi. I invite Pujari Charmi, student of Padmavati College. Charmi, are you online?
Yes, ma'am, I'm online. Am I audible, ma'am?
Yes, ma. Start your talk, ma.
A very good evening, good afternoon to everyone. This is P. Sharmi from SPW Degree and PG College. Today, I would like to present my abstract on the most pressing challenges of our time, the sustainable energy. The global energy demands are continuously increasing exponentially, driven by rapid industrialization and urbanization. As the conventional fossil fuels are depleting and their environmental consequences are increasingly evident, the world is shifting its focus towards the sustainable energy landscape. The energy has become the sole essence of the modern civilization, without which the progress halts and the innovation stagnates. It is not about doing less harm, but it is about doing more good. Sustainable energy is not just a buzzword, it is the change of how we power our world. As we grapple with the pressing challenges of winding natural resources and climate change, pursuing renewable sources like solar, wind, hydro energy has never been critical, harnessing the natural processes of our planet Earth. The planet is full with energy, free and clean. It is just out there waiting for us to set and sail over it. It offers a more sustainable pathway to reduce the carbon footprint and address the challenge of energy poverty that is being faced globally. A responsible renewable energy, can fix the right synergy between energy security, environment, and society. It can also strengthen the renewable ecosystem. Sustainable energy is a tapestry of modern innovations and challenges. However, researchers are going on to bring out innovative technologies to increase the efficiency and affordability of these resources to make them a viable alternative to conventional sources. There are being efforts are also put in to explore the current potential to meet the global demands and also to promote environmental stewardship. The cost of all these renewables have dropped down dramatically these days, making them accessible to many. The foremost thing that comes to our mind when we think of renewables is the solar. The sun is now resting on a new horizon of the energy era. The solar panels are widely seen from the rooftops of San Francisco to the deserts of India. In addition, the wind, hydro, biomass, geothermal, and hydrogen energies are introduced to unlock the door to our green, clean, and sustainable future. By embracing this paradigm, it will not only fuel our homes and industries, but also foster innovation, economic growth, and create a more cleaner and healthier planet. And in conclusion, this sustainable energy is becoming a revolution which will mark a major turning point in the human history, akin the Neolithic and the Industrial revolutions. Thank you, everyone.
Thank you, Charmi. Thank you. I invite Madhu Mohan, Mohan Baba University, Madhu Mohan. Sir, are you online? Madhu Mohan. Sir, Madhu Mohan, sir.
Share
just.
present.
Okay. Okay, sir. Okay.
Madam,
Sharing రాలేదు.
permission రాలేదు. Sharing permission ఇవ్వలేదు మేడం.
Sharing. Okay, sir.
మేడం పర్మిషన్ మీ నుంచి రాలేదు మేడం ఇంకా.
సార్ ఇచ్చున్నాం సార్, ఒకసారి షేర్ చేయండి సార్.
Is it visible, ma'am?
Yes, sir. Yes, sir. Continue, sir. Yes, sir. So start your talk, sir.
Madam?
Start your talk, sir.
Okay, ma'am.
Yes.
Okay. Good afternoon, all of you, madams and sirs. So this is Dr. Mohan, working in Mohan Babu University, Physics Department. I worked about in the field of dye-sensor solar cell. Instead of silicon solar cells, we are using dye-sensor solar cells because of low cost and mainly cost point of view, we are fabricating this type of solar cells. So it is not moving. Coming to the introduction, the various components of DSSC and working principle and photoelectrodes of DSSC and different applications of dye-sensor solar cells I'm going to discuss. So first, dye-sensor solar cells proposed by Michael Gressel. He is Swiss Federal Institute of Technology in Switzerland professor. He first invented this dye-sensor solar cell. This solar cell is working based on the principle of photosynthesis process. So when you're coming to the various components of dye-sensor solar cells, we have mainly three components. One is the working electrode and electrolyte and photocatalyst. Coming to the working principle, the sunlight is harvested, the dye molecules, dye is excited, then they transfer to the electron to the semi-crystalline material. Then that electron is moving to the outer circuit and reaches the catalyst. Then iodine molecules are reaches to this catalyst and dye is regenerated here. We synthesize different types of nanoparticles and nano rods, nanowires to preparation of these photoelectrodes. Among that, we used currently we are using this SDS synthesized materials. It was like a template. So these materials can give better efficiency compared to other materials because they have the high porous structures. So how we can prepare this zinc oxide working photoelectrodes? Generally, we synthesized powders are used to making the photoelectrode and adding of some Tritonics as a binder to make to deposit and allow to ultrasonic to get homogeneous mixing and spray this solution using FTO on the FTO substrate, maintaining at 150 degrees. And this type of solar cells we are using. We have many flexible solar cells we are making like this. So the Sony company and HANA other power generating windows, and you can see different types of colors by using different dyes. And Opera Sydney in Opera House also made by using these dyes and solar cells. And we can use various lamps, solar pans. In the Japanese company, they prepared this type of solar cells in the, and also we have the gadgets to make the charging of solar cells. We are making different type, using different dyes to make the solar cells for different colors, and we use windows. At present, we have the maximum efficiency is about only 15%. And coming to the market, dyes and solar cells growing technology is growing on market. It may reach about $50 to $70 million in 2030. Thank you. Thank you, madam.
Thank you, sir. Thank you, sir. Thank you, sir.
Thank you, madam. Thank you for giving the opportunity.
Thank you, sir. Thank you. The next participant is V. Lakshmi Devi, Department of Electronics. Are you online, ma'am? Lakshmi Devi, ma'am. Madam, start your talk, ma'am.
Okay, ma'am. I'm audible, ma'am?
Yes, ma'am.
Okay, ma'am. Thank you, ma'am. Good afternoon to all. Today I am going to present my paper on solar and cell technology, which is a renewable energy. The solar energy is the largest source of
clean and renewable energy amid climate changes. Solar energy utilizes the solar energy to convert the sunlight into electricity. The solar cells can be incorporated as an energy source in a wide variety of electronics and utilities. One of the significant advantages of solar energy is that it is a clean and renewable source of energy. The ever increasing demand of energy and electricity due to the Earth's expanding population and the consequent rising of atmospheric carbon dioxide levels caused by the use of fossil fuels may be the one of the reason for of the key factors that promoting the climate changes, that is called greenhouse effects. Unlike fossil fuels, solar power does not produce harmful emissions or contribute to climate changes. By utilizing the renewable energy sources such as energy from the sun, or our collective carbon footprint can be reduced. Hence, the research and development of the sustainable renewable energy sources are currently being prioritized. This article explains the development and changes in solar technologies over the years. It highlights the properties of 4 generations of solar cells, which are also called photovoltaic cells. Thank you for giving me this opportunity. Thank you, ma'am.
Thank you, ma'am. Thank you, ma'am. I invite next participant is Roshni, student of physics department. Roshni, are you online?
Yes, ma'am.
Start your talk, ma'am.
Hello, everyone. I'm Sheikh Roshni from 3rd BSc
Ma'am, start
MPCS.
your video also, ma'am. Start your video on.
Ma'am.
Okay, start your talk.
Today, I would like to discuss a crucial topic that affects our planet future. My topic is renewable energy versus fossil fuel energy. We all know energy is essential for our daily lives, but the way we produce and consume it has significant consequences. Fossil fuels such as coal, oil, and gas have been primarily source and energy of centuries. However, the depletion and harmful impact on the environment have led to a growing need for alternative energy sources. Renewable energy, including solar, wind, hydro, and geothermal power, offers a cleaner and more sustainable solution. It reduces greenhouse gases emissions, mitigates climate change, and ensures energy security. In this discussion, I would like to explore advantages and disadvantages of both renewable energy and fossil fuels and examine their landscape. I also touch on more innovative technologies. First of all, I would like to tell what is renewable energy. The renewable energy is derived from a natural resource that replenish themselves over time. Advantages of renewable energy. Environmental friendly. Renewable energy sources produce little to no greenhouse gas emissions, reducing their impact on climate. Abundant and sustainable. Their resource won't run out and inexhaustible. I would like to tell about fossil fuel energy. Fossil fuels like coal, oil, and natural gas are renewable energy sources formed by ancient organic matter. They released when they are burnt. Advantages of renewable fossil fuel energy. Fossil fuels produce concentrated energy, making them efficient for various applications. Our current energy system heavily rely on fossil fuels. Fossil fuels offer continuous power regardless of weather conditions. I would like to tell about the challenges that are made by the renewable energy. Solar and wind energy depend on weather and condition affecting consistent power energy and generation. And fossil fuel challenges are burning fossil fuels release pollutants contributing to air pollution, climatic changes, and habitat destruction. These resources are depleting and extracting can harm ecosystems. We know that coal, oil, natural gases, which are fossil fuels, these can be depleted at the end of the section. In conclusion, I would like to tell about renewable energy is superior choice compared to fossil fuel for several reasons, like sustainability. Renewable energy sources are sustainable and can be replenished naturally, unlike fossil fuels, which are finite. Environmental impact. Renewable energy generates little to no greenhouse gas emissions, reducing air pollution and mitigating climatic change. Fossil fuels are significant contributor to global warming. Innovation. The renewable energy industry drives innovation, leading to technology advancement and new opportunities. That's all. Thank you for giving this opportunity.
Thank you, Ma. Roshni. Next participant is Swarna Pooja, student of physics department. Are you online? Swarna Pooja or Prema? Anyone is online? Students of physics department, Swarna Pooja or Prema? Anyone are online?
Okay, ma'am. I think these two students are not online. So we'll close this session. Thank you. Thank you, Madam Taruna Teja, Madam. We'll start by 2:30. Is it okay for you, ma'am? Second session will start by 2:15, around 2:15 or 2:30, madam. Is it okay?
Yes, madam. Can I conclude by giving the report?
Okay.
Yes. So we had an informative forenoon sessions on importance of renewable energy systems. So here I would like to give a brief summary of the presentations. So Dr. Umarani discussed the impact of ICT on renewable energy adoption, highlighting how technology is advancing efficiency. And Dr. Sailama focused on solar thermal energy, showcasing its application, for example, like space heating and hot water systems. And Dr. Bharati provided an overview of solar cells, detailing various types of solar cells and ongoing research aimed to improve their efficiencies. And Dr. Nagamani addresses the energy saving programs in developing countries, mentioning the effects of industrialization, infrastructure needs, and the role of international funding. And Dr. Padma Srilata presented the use of solar energy in agriculture in India, demonstrating its benefits for enhancing the agricultural practices. And Dr. Madhu Mohan presented on the synthesis of porous dye-sensitized solar cells and showcasing some of the experimental results that demonstrate their potential for improved energy conversion. And Dr. Lakshmi Devi provided an overview of the development and changes in solar energy over the years. And we also had presentation from some of the students of Sri Padmavati Degree and PG College. Triveni, who presented on renewable energy solutions in developing countries in the context of climate change, mentioning the need for sustainable approaches to address the challenges. And Vaishnavi and Roshni compared the renewable energy with fossil fuels, discussed the issues related to the climate change, and emphasized that renewable energy is crucial for our future. And Charmi highlighted the importance of sustainable energies and the critical role for the solar panels in our transition to the more sustainable energy future. I would like to thank all the presenters for their information provided in the advancements of renewable energy sources in the future aspects. And I look forward to more discussions in the afternoon session. Thank you very much.
Thank you, madam. So we'll close this session.
Okay.
And we'll be continuing the session in around 2:30 or 2:15 p.m. As early as possible, we'll start the program.
Okay.
So I request all the attendees to join again for the next session. Thank you.
Okay.
Good afternoon, all of you. I welcome all the participants to join this second session. We'll start the program. I'm very happy to invite our resource person for this one-day international webinar, Dr. Yu Chalapati from South Korea. So I'll request my friend, Dr. D. Uma Meshri, to introduce our resource person.
Om Namo Venkateshaya. Good morning, everyone. Today we have the privilege of being in the presence of true visionary person in the field of environmental sustainability, Dr. Uppala Chalapati, very young and dynamic person. Dr. Chalapati now working as the assistant professor in the Department of Electronic Engineering, Egnam University, South Korea. It gives me great pleasure and an opportunity to introduce him as our today's resource person of the webinar. Dr. Chalapati has a great interest in the field of renewable energy materials, especially in thin film solar cells and photoelectrochemical water splitting. He worked as the research professor in the Department of Electronic Engineering, University of South Korea. He received his postdoctoral fellow from the Center for Optoelectronic Materials and Devices, Korea Institute of Science and Technology, Seoul, South Korea. Dr. Chalapati has more than 20 years of research experience in the field of solar cell fabrication. He has good experience on growth of binary, ternary, and quaternary compound semiconductor thin films by co-evaporation two-stage process. That is thermal evaporation, chemical bath deposition, sulfurization, chemical spray pyrolysis, and chemical bath deposition techniques. The second one is fabrication of compound semiconductor thin film heterojunction solar cells. Dr. Chalapati's another research skill is that he is expertise in the operation, maintenance, and troubleshooting of vacuum systems. He has good experience on GI-XRD and powder X-ray micro Raman spectroscopy, scanning electron microscopy, and energy dispersive X-ray spectroscopy, UV visible NRI spectrometer, which reflects spectral transmittance and reflectance, Hall effect for electrical properties, solar simulator for IV measurements of solar cells. Dr. Chalapati has fabricated copper antimony disulfide based thin film solar cells with efficiency of 2.5%. He is also expertise in the electro deposition of bright nickel, black nickel, and black chrome selective surfaces for solar thermal applications. Microfabrication of PBS-based IR detectors using photolithography, lift-off, etching, etc. techniques. He was the recipient of IUSSTF and DST BASc internship to carry out research work at University of Utah, USA. To his credit, he published nearly 50 peer-reviewed research papers on solar cell characterization and fabrication. This is all about brief introduction of our today's resource person, Dr. Yu Chalapati. Thank you for giving this opportunity. Thank you, one and all.
Thank you, Mama Shari. I welcome our resource person, Dr. Yu Chalapati, for this second session of this webinar, one-day international webinar on renewable energy sources and applications. We believe the insights and knowledge shared by Dr. Yu Chalapati will be valuable to each one of you. Okay, without any delay, we will start the program. Welcome, Chalapati sir.
Hello, madam. Am I audible? Hello?
Okay. Yeah, you are audible, sir.
But I cannot move my cursor in the presentation, madam. I have some problem. Sorry again. Can you help me how to share this my presentation? I cannot edit.
One minute.
Move it. Okay.
Sir, can you please move to the slides, to the PowerPoint page? Yeah, you can
Yeah.
click the second slide.
Yeah, but it's not going, sir. You can see.
Yeah, sir. You can click the second slide.
Yeah.
You are actually in the Google Chrome.
See, I am.
You have to just to
Uh-huh.
switch the app.
Switch
to PowerPoint.
Switch to PowerPoint. How can I do that? Here.
The downside in the taskbar, you can find the PowerPoint. You can click on that. Now you can click the slide 2. Just click on the slide 2. Actually, we can see your screen. We can see the first slide.
Yeah.
Thin film solar cells.
Okay.
If you click on the second slide, yeah, we can see your screen.
Uh-huh.
Yeah, we can see, sir. Yeah.
Oh, like that?
Yeah, sir. Just you can change the slide like that, and you can continue.
Oh, like this. Okay. Thank you so much.
Yes, sir.
Okay. Good afternoon, everybody. Thank you very much for giving me this opportunity to join this webinar, and especially Jayshree Madam. She is my senior. We did PhD together. Can I see the window, sir? Sorry. Hello?
Sir, your slides are visible, sir. You can go to the next one.
Okay, today my topic is thin film solar cells and an overview. So my name is Tirupati. I'm currently working as a research professor in Department of Electronic Engineering, South Korea. So in this presentation, I will give you some fundamentals about the thin film solar cells and the advantages compared to crystalline silicon solar cells. And the research work that I am doing in my current lab. So coming to the introduction, so energy is essential for economic development and growth, you know. So this energy, basically, we get this energy from fossil fuels, coal and natural gas. But currently the cost of oil and natural gas are increasing at a rapid rate because of their rapid consumption, because of their demand and limited supply. This can lead to global shortage of automobile fuel and cause problems in the transport sector. So the release of greenhouse gases by burning fossil fuels has increased environmental concerns, which means it causes environmental pollution. Hence, there is a search for alternative energy, need to search for alternative energy sources to resolve the energy crisis without causing any pollution. Solar energy is an attractive option. Alternative energy source which energy needs without causing environmental pollution. So basically, what is a solar cell? A solar cell is a device that converts solar energy into electrical energy. Basically, it is a PN junction diode that works on the principle of photovoltaic effect. A photovoltaic effect is nothing but it converts photons into voltage and current. So a solar cell can be seen here. So it has a P-type layer, an N-type layer, bottom contact and top contact, and some anti-reflection coating. So when sunlight, how does it work? How a solar cell can work? Cell absorbs the light absorption. Then light absorption creates electron hole pair generation. Then the created electron hole pair, they get separated by built-in electric field present in the PN junction. And the separated electron hole pairs, they collected by the top and bottom contacts. This is how a solar cell works. Since it generates, it works on the principle of photovoltaic effect. It's also called a solar cell. Photovoltaic cell. Now, if you see the solar energy spectrum, the solar energy spectrum is a range of wavelengths of energy emitted by the sun from gamma rays to the radio waves. It's made up of photons with different wavelengths, which define the shape and intensity. So, Earth receives 1.37 kilowatts per meter square of power, and the solar spectrum, if you see, it extends from 0.3 micrometers to 2.5 micrometers. Out of the solar spectrum, 49%, the solar energy spectrum contains 49% of IR radiation, only 46% visible radiation, that is from 400 to 700 nanometers that we can able to see with our naked eye, and 5% of UV radiation. So the solar cells usually they are fabricated with semiconductor basically. Semiconductor is a material that where it has a valency band and a conduction band separated with some energy difference. This minor energy difference, minimum energy difference, is called a band gap. Based on the transition from the valence band to the conduction band, these semiconductors are classified into direct band gap and indirect band gap semiconductors. If the transition from the top of the valence band to the bottom of the conduction band takes place at the same momentum as shown in here, it's a valence band and a conduction band. The transition from the top of the valence band to the bottom of the conduction band occurs at the same momentum. It is called a direct band gap semiconductor. When the transition happened from the top of the valence band to the bottom of the valence band at different K value, this is called an indirect band gap semiconductor. In direct band gap semiconductor, the momentum is constant before and after transition, whereas indirect band gap semiconductors, the momentum is not constant before and after transition. The examples are gallium arsenide for direct band gap, gallium arsenide, cadmium telluride, or direct band gap semiconductor materials, whereas indirect band gap, silicon, germanium, those are the indirect band gap semiconductors. These semiconductors can be fabricated in single crystalline, polycrystalline, amorphous. If the atomic arrangement in a solid state material is periodic across the whole volume, like atomic arrangement is very periodic like this, they are called single crystalline materials or semiconductors. If their periodicity is limited to certain regions, they are called polycrystalline semiconductors. If there is no periodicity, like the atomic arrangement is very irregular, they are called amorphous semiconductors. This shows the grain size in single crystalline, polycrystalline, multicrystalline, amorphous materials. For single crystalline materials, the grain size varies from 10 micrometers more than centimeters range, 100 centimeters. Whereas polycrystalline materials, the grain size varies from 1 nanometer to 10 micrometers. In polycrystalline, they may be microcrystalline, nanocrystalline. If the grain size is in the range of 1 to 100 nanometers, they can be called nanocrystalline. The grain size is from 0.1 to 1 nanometer range. They are called amorphous semiconductors. Let us see how the interaction of light in semiconductor, because this is very much essential to determine the thickness of a solar cell material. So if you want to make a solar cell, you should determine how much thickness it is required. Let us say a semiconductor with a thickness of T that has an optical absorption coefficient alpha. The determines how much conductor before it is going to be absorbed. So if we incident a light with intensity I0 on a semiconductor, Usually what happens when some light incident on it, there is a possibility for reflection, absorption, and transmission. So if you see the intensity of the transmitted light, IT is the intensity of the transmitted light, I0 is the intensity of the incident light, and this we can express as IT is equal to I0 e power minus alpha t, where alpha is the absorption coefficient of the semiconductor, t is the thickness of the semiconductor. So the amount of the light absorbed by the semiconductor can be a difference of the intensity of the incident light minus intensity of the transmitted light. So if we replace IT by I0 e power minus alpha t, so we are going to use for solar cell. Suppose if the thickness of the semiconductor is 1 by its absorption coefficient, then if you replace alpha t by 1 by alpha here, it will turn into 1 minus e power minus 1. 1 minus e power minus 1. E power minus 1 can be written as 1 by e power 1. So e power 1 value is 2.71. So 1 minus 1 by 2.71 gives 1.71 by 2.71. It gives 0.63. So IA is equal, amount of absorbed light intensity is equal to 63% of the incident light. So if the thickness of the semiconductor is 1 by alpha, so it absorbs 63% of the incident light. If the thickness of the semiconductor is 2 by alpha, it absorbs 86%. E power 2 is to 7.38. If you substitute this value, you will get 0.86, 86%. If the thickness of the semiconductor is 3 by alpha, then it absorbs 95% of the incident light. So you can see the optical absorption coefficient of different semiconductor. So here, gallium arsenide, cadmium telluride are the direct band semiconductors. Germanium silicon are the indirect band gap semiconductor. For silicon, which has a band gap of 1.1 electron volt, it has an optical absorption coefficient of 10 power 2, that is 100 centimeter inverse. Similarly, for germanium, if you see germanium has 1.7 electron volts, it has a optical absorption coefficient of 10 power 2, which is 100. So let us say for indirect band gap semiconductors, if you replace T is equal to 1 by alpha here, alpha is 10 power 2 for silicon or germanium. 1 by 10 power 2 is nothing but 10 power minus 2 centimeters, that is 10 power minus 4 centimeters, that is equal to 100 micrometers. Let us say silicon with 100 micrometers, silicon solar cell with 100 micrometer thickness, it absorbs only 63% of the solar spectrum or incident light, solar spectrum. Similarly, if it is 200 micrometers, it absorbs 86% of the light. If it is made with 300 micrometers thickness, a solar cell, silicon solar cell or germanium solar cell, they absorb only 95% of the, absorb 95% sunlight. Let us see a direct band gap semiconductor, gallium arsenide. It has a band gap of 1.45 and its absorption coefficient is this one. It is absorption coefficient 10 power 4. Similarly, cadmium telluride, 10 power 4 centimeter inverse. If you replace alpha with 10 power 4, so 1 by 10 power 4 will give us 10 power minus 4 centimeter, that is equal to 1 micrometer. For direct band gap semiconductors, gallium arsenide, cadmium telluride, with 1 micrometer thickness, it absorbs 63% of the incident light. If you make it with 2 micrometers, it absorbs 86%. 3 micrometers, it absorbs 95%. So indirect band gap semiconductors, the single crystal silicon solar cells, they are germanium solar cells. They are made with indirect band gap semiconductors. The thickness we require from 200 to 300 micrometers, whereas for gallium arsenide and cadmium telluride, direct band gap semiconductors, the thickness is required only is 1 to 3 micrometers is enough to absorb all the incident light, most of the incident light. So choice of a semiconductor for solar cells. If you want to choose a semiconductor for a solar cell, what are the properties of the solar cell? It should have an optimum energy gap. A semiconductor should have optimum energy gap. It should have high optical absorption coefficient. It should be electrically conductive, and it should be feasible for the process. And the element should be relatively abundant, and the element should also be environmentally friendly. This is the crystalline silicon solar cell. This is a real device we can see here. And if you see this cross section, what are the various layers that are present in this crystalline silicon solar cell? It has a back contact, possibly is aluminum or some other some metals, silver, and a P-type layer, N-type layer, and a anti-reflection coating, top grid contacts. Okay, see, we can see here a PN junction formation. How it works. Okay, a PN junction formation for silicon. You know, when we dope a trivalent impurity to the intrinsic silicon, it converts P-type semiconductor. Similarly, when we dope a pentavalent impurity, it has 5 valence electrons to the silicon, it converts N-type. When we join these P-type and N-type together, there is a depletion region get formed that is called a PN junction, that is called PN junction. When light incident, this is the depletion region, it has some built-in potential. When light falls on the this junction, it creates electron hole pairs. This electron hole pair gets separated by the built-in potential that is available in the PN junction, and they get collected. They get collected by the external load. This is how the solar cell works. So there are factors limiting the efficiency of the solar cells. Usually, when sunlight falls on any material, there are 3 phenomena, right? Reflection, transmission, absorption. Similarly, in solar cell, there is a reflection loss. Reflection loss from the top surface, from the metal contacts that we use, and if the surface is rough, that will also make reflection losses. So to reduce the reflection losses, the top surface, we should make the top surface should be very uniform, and also people use anti-reflection coatings. The absorption losses. See, solar light energy, it contains photons, right, from 0.5 to 4 electron volts. So let us take silicon solar cell as an example. Silicon has band gap of 1.1 electron volt. Well, photons with 0.5 to 4 electron volt that incident on the solar cell, the photons from 0.5 to 1.1 electron volt, they doesn't absorb because the energy is very less. So that is the loss, absorption loss. Some part of the solar spectrum get lost. Then the photons that has energy equal to 1.1 electron volt, they get absorbed, and excess electrons, excess energy, like 2 electron, let us say 2 electron, high energy photons. For silicon, just only we need 1.1 electron. Higher energy, if it is a 2 electron volt photon, out of 2.2 electron volts, 1.1 electron volt energy is successfully utilized, and excess energy will heat the device. That is partial utilization of the absorbed energy. So incomplete collection of the electron hole pair by the junction. So the generated electron hole pairs usually they get scattered by the grain boundaries. If the diffusion length of the charge carriers is less, if the diffusion coefficient is less, then they get recombined. So that is called incomplete collection of the electron hole pairs. There will be voltage factor losses. Usually solar cell, the voltage for any solar cell, it is approximately its band gap divided by 2. We can get, let us say, silicon 1.1. Approximately, if we divide easy by 2, band gap by 2, we get 0.55 volt. If the device quality is not good, there will be voltage factor loss. Fill factor will give us the how best the device, the solar cell is. If the device quality is not good, there is a fill factor loss, series resistance, because there are many layers in the solar cells, right? The absorber, the buffer, the top contact, bottom contact, anti-reflection coating. So each layer will give some resistance. So that is also series resistance. So these are the factors that limit the efficiency of a solar cell. So yeah, so that is how crystalline silicon solar cell, because their absorption coefficient is less. Okay, just a minute. Because of their low absorption coefficient and also fabrication cost, crystalline for silicon solar development of silicon solar cells, the fabrication cost is very high. So that's why people go for thin film solar cells. Thin film solar cells require very low material consumption and manufacturing, low manufacturing cost also. The thin film solar cell basic structure is look like this. Usually it is prepared on a glass substrate. It has a back contact molybdenum, an absorber layer, a buffer layer, an absorber layer with a band gap should 1 to 1.6 electron volt, a buffer layer with a band gap greater than 3 electron volts, and a window layer, a top front contact layer. The basic structure of a thin film solar cell is like this. So how to choose? Criteria for selection of heterojunction pair. The crystalline silicon solar cell, the solar cell is made with the same kind of material that is called homojunction solar cell. If you prepare a solar cell with two different materials, P-type material is different, N-type material is different, so it's called a heterojunction pair. And the criteria for choosing P and N layer should be the band gap of the absorber layer should be 1 to 1.6 electron volts, buffer layer should be 3 electron volts, and the absorber should be P-type, the buffer should be N-type, and there should be a very small lattice mismatch, and there should be lower electrical resistance to contacts, and the material should be good in supply. Availability could be good in supply. They must be cost competitive. The material should be non-toxic, and the cell should be non-degradable. These are the prime requirements for the selection of the solar cell. Plus, there are various types of solar cells so far developed: amorphous silicon, thin silicon solar cells, gallium arsenide solar cell, cadmium telluride, cadmium sulfide thin film solar cells, copper indium selenide, cadmium sulfide solar heterojunction solar cells, copper indium gallium selenide, CDS thin film solar cells, CZTS, CDS heterojunction thin film solar cells. See, silicon. In the crystalline silicon, band gap is 1.1 electron volt, and it has absorption coefficient 10 power 2. But if you prepare silicon amorphous, and the absorption coefficient also increases to 10 power 3 centimeter, 10 power 3 centimeter nodes range. So silicon is also amorphous silicon is also prepared in thin film solar cell configuration like this. They use glass, FTO. This is a fluorine doped tin oxide, a P-type amorphous hydrogenated amorphous silicon, intrinsic amorphous silicon, N-type amorphous silicon, and a transparent conducting oxide, and finally aluminum or silver bottom contacts. So CDTE, CDSC thin film solar cell configuration is look like this. So they prepare a FTO layer on top of the glass substrate, then a cadmium sulfide layer with a thickness of 60 to 200 nanometers, a cadmium telluride absorber layer, finally carbon paste with the copper or other metals. And these CDTE solar cells achieved efficiencies of 23% at the laboratory level. And also another view of the PDT solar cell you can see here. Same, it can band gaps of cadmium telluride, cadmium sulfide, and this cadmium telluride has a poor contact quality. This is the one of the drawback of cadmium telluride solar cells, and also toxicity. So the efficiency is very high. It achieved 23%, but cadmium is highly toxic. So it's not good for the environment. So copper indium gallium selenide, thin film solar cell. So this is the architecture of copper indium gallium selenide. It consists of glass substrate, a molybdenum layer, molybdenum bottom contact, a CAGS absorber, a cadmium sulfide buffer layer, and a transparent conducting oxide, and finally top metal contacts. So the fabrication of these solar cells can be carried out by using a three-stage process called sputtering plus cellularization, a CDS deposition by chemical path deposition, zinc oxide by reactive magnetic sputtering. They prepare like this. The CAGS thin film solar cells achieved high efficiency of 23%. They have high radiation tolerance and at high temperature stability, and this is a proven technology. However, it also has costly, expensive indium, scarce gallium. So this is not good for this technology. It doesn't run for long run. So this shows the fabrication of CAGS modules. So CAGS module fabrication involves substrate cutting, cleaning, followed by back contact formation, patterning of the back contact, absorber layer deposition, buffer layer deposition by chemical bath deposition, patterning of the absorber buffer layers, followed by window layer formation, patterning, and finally electrical contact and encapsulation. Sorry. So far these single crystalline silicon and thin film solar cells, they are single junction solar cells. Single junction solar cells, the efficiencies achieved are very less. I mean, the theoretically possible efficiency for the single junction solar cells are 30%, less than 30%, and practically achieved efficiency for CIGs and CDTE solar cells are close to 24%. So in order to enhance the efficiency of the solar cells close to 50%, there is a tandem solar cell concept was introduced. This tandem solar cell concept is nothing but the adding of these stacking of the three to four different kinds of solar cells with different band gaps, such that at the top of the photons more deeper into the material. So that the higher energy photons, they get absorbed initially whenever they falls on the semiconductor. So the higher energy for, let us say, gallium indium phosphide, if it has a band gap of the gallium phosphide. If you see the gallium phosphide, it has a band gap of more than 2 electron volts. If you prepare a top layer, a top solar cell with 2 electron volt solar cell, it absorbs from 2 to above higher energy photons successfully. And if you prepare middle cell with a band gap of 1.5 or 1 electron volt, it absorbs those photons successfully. And if, let us say, germanium has 0.7 electron volt. If it is a germanium solar cell, it absorbs lower energy photons successfully. This is how it enhances the absorption of solar spectrum and enhance the efficiency. And this shows, this is the amorphous silicon dual junction solar cell. So amorphous silicon, it has 1.8 electron volts. This is the amorphous silicon solar cell. It has FTO, P-type hydrogenate amorphous silicon, intrinsic amorphous silicon, N-type amorphous silicon, and Here it is germanium doped amorphous silicon. With germanium doping, the band gap can be decreased to close to 1 electron volts. So 1.8 to 1 electron volt, it enhances the efficiency. So these are the gallium arsenide thin film solar multi-junction solar cells. Here it's a three solar cells. Three cells, three tandem cells. Bottom cell is made with the gallium arsenide, which is with the band gap of 1.4 electron volts, and middle is a tunnel junction, gallium arsenide tunnel junction, and top is a gallium indium phosphide, which band gap close more than 2 electron volts, I guess. So, and this shows the solar cell efficiencies of the different types of solar cells: multi-junction, crystalline silicon, thin film solar cells, and emerging photovoltaics. If you see the multi-junction solar cell, the efficiency of the multi-junction solar cell are close to 50% or 48%. This is a four junction concentrated solar cell. And if you see crystalline silicon solar cell, they achieved efficiency of close to 28%, 26%. And thin film solar cells technology, if you see, with a 45 years of research effort from 1975 to 2023, the CIGS solar and cadmium telluride solar cells reach efficiencies of 23% with 40% of research effort. So there is emerging one, perovskite solar cell. It reached within a span of 10 years, it reached close to 28% efficiency. So in our laboratory, I have developed a new solar cells based on a new materials, new compound semiconductors, copper, antimony sulfide based thin film solar cell. So these are the cross-sectional views of the prepared solar cell. You can see here, it has a molybdenum on top of the glass substrate. Copper, this is the absorber copper, antimony sulfide, and I prepared cadmium sulfide buffer layer here and zinc oxide intrinsic layer. Finally, top the ITO, transparent conducting oxide, and finally silver metal contact. So this solar cell, this absorber, I prepared by using a two-stage process by thermally evaporating copper, antimony, metal precursors and sulfurizing them at 450 for 1 to 10 minutes. And this, you can see the microstructure, the cross-section of the absorber here. The CUSB-S2 had highly crystalline, large grain, and single phase, and it has a band gap of 1.42 electron volts. And of course, is a direct band gap semiconductor, which has optical absorption coefficient greater than or equal to 10 power 4 centimeter inverse. And the best solar cell exhibited 2.5% efficiency, VOC of 56.7 millivolts, current density of 13.8 milliampere per centimeter square, and a fill factor of 31.6%. This low fill factor indicate the poor quality of the fabricated cell structure. So we have to optimize the cell structure to improve the efficiency of this copper antimony sulfide based solar cells. Similarly, I have developed a silver antimony based thin film solar cells using this two-stage process. And this is the cross section of the solar cell that I prepared. And we can clearly see this is the architecture: molybdenum, absorber, buffer, and TCO, top silver contact. And we can see the how good the quality of the absorber or its thickness across its thickness. And this solar cell exhibited just 1.1% and VOC of 519.6 millivolt, current density of 6.63 milliamperes per centimeter square. And fill factor, similarly low fill factor, which indicates poor quality of the prepared structure. Similarly, we also prepared AG3 S3 based thin film solar cells with very low efficiency, 0.3%, and a high fill factor with improved fill factor. And we can see the device architecture here. And this is the JV curve. And device architecture here has molybdenum, absorber, cadmium sulfur, ITO, silver. Similarly, I prepared many different kinds of ternary, quaternary, binary, compound semiconductor thin films for their application for solar cells. Thank you very much for your kind attention. Hello, madam.
Thank you, Dr. Tirupati. Hello. Hello.
Yes, madam. Hello, madam.
Your talk is over.
My finished, madam. Talk is finished. And
Okay. Thank you. Thank you very much. Thank you very much, Dr. Chalapati, for your valuable and very informative details about the solar cell fabrication, right from the beginning of preparation, how to characterize, how to fabricate a solar cell. Everything you explained in a very good manner and very informative session also. Thank you so much for your valuable information regarding the solar cells.
Yeah, madam. Thank you.
I request attendees or participants, if you have any questions, please raise your hand so that you can make a contact with our resource person. Is there any questions? If you have any questions, please raise your hand. Okay. If not, shall I ask you one question, Chalapati sir?
Yeah, sure, madam. You can call me Chalapati, madam.
Okay. Thank you. So from my side, what is the latest efficiency of a solar cell? And which type of material can we use for the heterojunction solar cells? Latest efficiency. What is the efficiency?
There are many solar cells, madam. The best efficiency is CIGS. Heterojunction solar cells, CIGS.
CIGS. So what is the efficiency? Yes. Percentage of efficiency?
Close to 23%. 23%, madam.
Okay. Thank you, sir. What are the heterojunction? When you said it's a heterojunction solar cell, what are the materials? I mean, apart from this CIGS.
Yeah, there are different kinds of material from binary to ternary. Yeah, madam.
No, ternary. Latest ternary.
Yeah, binary
compound.
also.
Ternary
is Cu to SnS3, madam. Cu to SnS3 is there. Yeah, Cu,
I know that. What is the latest?
There are very latest means which material? I think there are many materials, madam. We cannot say.
Okay. So near lab, you are
each has its own.
Yeah, thank you.
Yeah, madam. Copper antimony sulfide.
Jeevan Kumar, I think he has raised that. And so please, sir, unmute your.
Yes. Okay. Thank you so much for your interesting talk. I understand a few points which I really disconnected with solar cell research. My question is like, you have explained the tandem concept, right?
Yes, sir.
So the tandem concept I think I know that it could be adapted for every solar cells. So like even Dyson Stray solar cells too, right? Not just thin films.
No, sir. There should be compatibility. Not for Dyson Stray solar cells. 3-5 based solar cells are.
In what way it cannot be adapted for Dyson Stray solar cells? Can you explain that?
Yeah, because there is a criteria, sir. There should be less lattice mismatch. The band gap. Band gap criteria, right? The top cell should be higher band gap. Middle cell should be somewhat lower. Lower, still lower means still lower. So this criteria should be satisfied, sir.
Okay, but in Dyson Stray solar cells, what if I could make a surface coating which can absorb higher wavelength, for example, higher energy, for example, then can it be not possible in Dyson Stray solar cells? Because I rarely see that this tandem concept in dye-sensitized solar cells. That's why I mean to ask.
It's not, I think, not possible. If you see here, it's a solar cell efficiency table I'm showing here. Here, dye-sensitized solar cell, there is no tandem concept. You can see multi-junction solar cells here. There is no such kind of tandem solar cells in dye-sensitized concept. Dye-sensitized concept is different.
Yeah. Okay.
As far as I know, I think not possible, sir.
Okay. Okay. I understand. Thank you. Thank you so much.
Yes.
Okay, sir. Thank you very much. Shall we go to the next session? Okay, thank you, Dr. Chalapati, sir. We'll continue the next sessions, scientific sessions and the paper presentations. I request our Dr. Jeevan Tarunateja to share this session. Ma'am, please. Dr. Teja, madam. I request Dr. Tarun Teja, madam, to share this second session, scientific session.
Hello, Tarun Teja, madam. Are you online? Hello, madam. Tarun Teja, ma'am.
Yes. Am I audible?
Join, ma'am. Yes, ma'am.
Okay. Good afternoon, everyone. Welcome to the afternoon paper presentation session of the one-day international webinar on renewable energy sources and application. And I'll be chairing this session. We have several presentations lined up from now. Each one is limited to 3 minutes and each speaker should give an overview of their work. After the presentations, if anyone have questions, please ask at the end of the session. Now let's get started with our first speaker. Thank you.
Okay, ma'am. Thank you, ma'am. I invite Chandrasekhar to this session. I invite Chandrasekhar C. Chandrasekhar Reddy, Atmospheric Science Laboratory, Department of Physics, Yogi Vemana University. Sir, Chandrasekhar sir, are you online? Sir Chandrasekhar sir, are you? Sir, start your talk, sir. Chandrasekhar sir. Sir, right? Yes, sir. Sir, you unmute and start your talk, sir. Chandrasekhar sir. First, you unmute and start your talk, sir.
Okay.
Okay, sir. Okay, sir. Please on your video, sir. Okay, sir. Start your talk, sir.
Okay, good afternoon, madam. Good afternoon to everyone. My name is C. Chandrasekhar Reddy, a research scholar, Department of Physics, Renewable University. Today I will explain about the hydrogen fuel production technologies for sustainable development. First of all, what do you mean by sustainable development? The sustainable development is defined as to meet the needs of present generation without compromising the ability of future generation to meet their needs. This statement was given by G.H. Brundtland, Norwegian Prime Minister. Now, first of all, outline of our presentation. First of all, introduction of hydrogen energy, then production of hydrogen energy, storage process, distribution of hydrogen energy, and applications of hydrogen energy. First of all, introduction. Now, hydrogen is the most abundant element in the universe, and it is the simplest and lightest element. Next, hydrogen is made up of just like one electron and one proton. Next one, it is the first element in periodic table. Normally, it is available in gaseous state. Madam, am I audible? Hello.
Yes, sir, audible. It's clearly audible.
Okay, thank you, madam.
Continue, sir.
Okay. Hydrogen, the properties, it is odorless, tasteless, colorless, and non-toxic component. Non-toxic means does not produce any harmful effects due to environmental. The next one, hydrogen burns with oxygen. It will be produced some amount of energy in the form of heat and produce water. That is 2H2 plus O2 gives rise to 2H2O plus some amount of energy. The next one, the production of hydrogen. Here are different ways to produce the hydrogen gases by using different resources like nuclear energy resources, renewable energy resources, and fossil fuels. By using directly or indirectly, we can produce electricity. That electricity are used to produce hydrogen. Like, for example, if you use the heat energy from nuclear energy, it will be converted into thermolysis of water, which can produce hydrogen. Next, second one, for example, photolysis of water. Photolysis of water. By using solar energy, we can divide hydrogen plus oxygen of water, like that. The next one, storage of hydrogen. This is the critical. The production of hydrogen is, when compared to others, is easy, but storage and distribution of is very critical in widespread adoption. There are few technologies are used to store the hydrogen energy. First one, compressed hydrogen gas. Second one, liquid hydrogen and liquefied hydrogen. Here, the difference between these two, the liquefied hydrogen has more expensive when compared to liquid hydrogen. Then the process of liquefaction, some amount of approximation 20 to 30% of hydrogen gases reduced or lost. The next third one, metal hydrates, chemical hydrates, adoption, underground storage. These methods, we can store the hydrogen gas in metal hydrates. The next one, development in storage technology to aim the improve the efficiency, then reduce the cost and enhance the safety standards. The next, distribution of hydrogen. Hydrogen can be distributed at both liquid and gaseous state, depends upon their requirement. Hydrogen fuel in the gas phase could be transferred via high pressure tube trailers. Second one, the liquefied. This is the liquid or liquefied gas. Liquid hydrogen can be transported via roadways, railways, and ships. Next one, overall explanation of hydrogen energy. This is the production, distribution, this is the storage process. We can produce the hydrogen by using these all resources like fossil fuels, coal, oil, biomass, solar energy, and wind energy. They directly or indirectly produce hydrogen. This hydrogen can be converted into either liquefied or gaseous state. That These two processes are converted into transportation process. First one, tube trailer through pipeline. The gas transportation in these two ways. But liquefaction of hydrogen can be converted into transport into cryogenic tanks. Then the final use in different sectors like grid, power industry, refilling, building process. The next one, applications of hydrogen energy. Hydrogen can be utilized in various sectors. Why prefer the hydrogen energy is nothing but it having the high efficiency and zero emission. The main concept of sustainable development means to protect the environment without production of any pollutants. So first one, hydrogen can be used in various sectors, including transportation. Present, most of the vehicles are depends on non-renewable energy resources like fossil fuels, petroleum fuels. The next one, industry means chemical process and refining and power generation for fuel cells. Then fuel cell technology converts hydrogen energy into electricity with high efficiency. Most of the energy storages, energy generation process, the efficiency is very low. For example, if we can use 100% of solar energy, we can convert only maximum of 20 to 25% of efficiency. The next one, despite its potential, hydrogen fuel technologies face challenges such as cost competitive, infrastructure development, and public acceptance. Thank you. Ma'am, completed, ma'am.
Sir. Thank you, sir.
Okay, thank you.
Next, I invite Kishore Kumar, sir. Kishore Kumar, sir. Mohan Babu University, Kishore Kumar. Mohan Babu University, Kishore Kumar. Sir, are you online? Next. Next participant is, I invite Dr. M. Kumudini, lecturer in Commerce, SPW Degree College. Kumudini madam? Kumudini madam, are you online? Kumudini? Sunita madam, are you online? Sunita madam?
Yes, Suma.
Lecturer in Commerce.
Yes,
Madam, are
Suma.
you online?
Yes.
Okay, madam. Okay, madam. You present your paper, madam.
Oh, okay.
First unmute, madam. Next, start your talk.
I think I am unmuted. Okay.
Okay, madam. You are audible. You are audible. Start your talk.
Okay. Om Namo Venkatesaya. I am very thankful to our principal madam, Dr. Narayanamma madam, and Dr. Uma madam, HOD of Department of Physics, for giving this great opportunity. My topic is energy saving programs of developing countries. That is, renewable energy is energy from renewable natural resources that are replenished on a human timescale. The most widely used renewable energy types are solar energy, wind power energy, and hydropower. Bioenergy and geothermal power are also significant in some countries. Renewable energy installations can be large or small and are suited for both urban and rural areas. So this is the most important. Another energy, that is fossil fuels. For example, coal, oil, and gas are non-renewable resources that take hundreds of millions of years to form.
Fossil fuels, when burned to produce energy, cause harmful greenhouse gas emissions such as carbon dioxide. For decades, economic and scientific organizations have urged leaders to create policies to promote renewable energy as part of vital global efforts to fight climate change. So, in addition to reducing carbon emissions, large-scale renewable power projects also provide demonstrable economic benefits for investors, governments, and especially consumers who need reliable. So, generating renewable energy creates for lower emissions than burning fossil fuels. The main motivation to replace fossil fuels with renewable energy sources is to slow and eventually stop climate change, which is widely agreed to be caused mostly by the greenhouse gas emissions. So, this is the most important one. While developing countries may not have the public funds to build sufficient new infrastructure, well-crafted, large-scale renewable power projects can attract the private investment needed to get plants up and running. In developing countries, lack of access to finance under reasonable terms makes the costly upfront investments in renewable energy unaffordable. So, but nowadays, fortunately, there has been increasing interest in building modern, large-scale infrastructure. In 2020 alone, the public and private sectors invested over $300 billion in renewable energy. Although annual investments in clean energy need to more than triple by 2030 to reach net zero emissions by 2050. I am very thankful to Dr. Uma Madam, HOD of Physics Department.
Thank you, madam. Thank you, madam.
Okay.
Next, I invite Kumudini, madam.
Yes,
Are you
ma'am.
online? Yes, ma'am. Audible, you can start your talk, ma'am.
Okay, madam. Om Namo Venkateshaya. Good afternoon, everyone. Today, I will present a brief overview of sustainable energy, a comprehensive overview of renewable energy sources in India and their current status. Sustainable energy is essential for addressing climate change and ensuring long-term energy security. Unlike fossil fuels, which are finite and harmful to the environment, sustainable energy comes from sources that are naturally replenished and have minimal ecological impact. They are not only essential for reducing greenhouse gas emissions, but also play a key role in achieving energy security and promoting socio-economic development. Major types of sustainable energy include solar, wind, hydro, geothermal, and biomass energy. So, characteristics of renewable energy: unlimited power source, low carbon footprint, minimal waste generation, diverse applications. When you see the need and importance of renewable energy, environmental conservation, energy security, socio-economic development. So now we will see renewable energy in India. India has emerged as a global leader in renewable energy with significant progress across various sectors. India has made significant strides in the renewable energy sector, becoming a global leader in this domain. Renewable energy constitutes about 33% of India's total energy consumption. This shift is driven by both environmental concerns and the need to meet growing energy demands. Now we will see the solar energy in India. Solar energy is at the forefront of India's renewable initiatives. The country has set ambitious targets under the National Solar Mission, aiming for 100 gigawatt of solar power capacity by 2030. Key projects include the Reva Ultra Mega Solar Park and the Badla Solar Park, which are among the largest in the world. These initiatives not only contribute to India's clean energy goals, but also drive significant technological advancements and investments in the solar sector. Next one is wind power. So wind is another cornerstone of India's renewable energy strategy. India is the fourth largest producer of wind energy globally, with major installations in Tamil Nadu, Gujarat, and Maharashtra. Government policies, including incentives and supportive frameworks, have played a crucial role in expanding wind energy capacity. Hydroelectric power. It plays a significant role, particularly in the northeastern and Himalayan regions. India's hydroelectric potential is substantial, with ongoing development of both large-scale and small-scale projects. While hydroelectric power offers a reliable and stable energy source, challenges such as environmental impacts and long development times need to be addressed here. Geothermal energy. Although still it is in the initial stage of development, India is exploring geothermal resources in regions like the Himalayan belt and the Andaman and Nicobar Islands. Biomass energy. Widely utilized in rural areas, biomass energy from agricultural and forestry residues is a key component of India's renewable strategy, despite challenges related to emissions and food competition. Biomass energy supports rural economies and provides a means to manage waste. Despite these advancements, India faces challenges such as high initial cost, infrastructure needs, and the need for coherent policies. India ranks fourth in the world in renewable energy installed capacity. China ranks first and produces 31% of global renewable electricity, followed by the United States, Brazil, Canada, and India. However, with over 4,500 renewable energy companies, India is well positioned to lead in this sector. India is a hub for green energy innovation and development. Notable companies include Adani Green Energy Limited, Renew Energy, Tata Power Renewable Energy, Sterling and Wilson Renewable Energy Limited, Reliance Industries Limited, Hindustan Power Projects Private Limited, Suzlon Energy Limited, NTPC Limited, Indian Oil Corporation Limited. Now, when you see the conclusion, it can be concluded that sustainable energy is vital for mitigating environmental impacts and ensuring energy security. India's progress in renewable energy reflects its commitment to a greener future, supported by strong investments and policies. India's progress in renewable energy is remarkable, driven by ambitious targets, significant investments, and supportive policies. The country's commitment to expanding its renewable energy capacity highlights its dedication to a sustainable and environmentally friendly energy future. I am very thankful to the Department of Physics for giving this wonderful opportunity. Thank you, one and all.
Thank you, ma'am. Thank you. Kishore Kumar, sir, are you online? Next, I invite Kishore Kumar, sir. Are you online? Next, P. Mahita, student of political science. P. Mahita. P. Mahita, are you online? P. Mahita, student of political science. Next, myself present a paper. I am Dr. D. Uma. I am Dr. D. Uma Maheshwari, lecturer in physics, SPW degree and PG college. Today's my topic is the purpose of solar panels in energy production. Solar energy is inexhaustible, freely available, and clean source of energy generation. The solar PV system generates variable output. Its operation depends upon the solar irradiance. The article provides information about solar panels and energy systems. A solar panel is a device that converts sunlight into electricity by using photovoltaic cells. PV cells are made up of materials that produce excited electrons when exposed to light. The electrons flow through a circuit and produce direct current electricity, which can be used to power various devices or be stored in batteries. Solar panels are also known as solar cell panels, solar electric panels, or PV modules. Solar panels are usually arranged in groups called arrays or systems. A photovoltaic system consists of one or more solar panels, an inverter that converts DC electricity to alternating current electricity, and sometimes other components such as controllers, meters, and trackers. Most panels are in solar farms which supply the electricity grid, as can some rooftop solar. Some advantages of solar panels are that they use a renewable and clean source of energy, reduce greenhouse gas emissions, and lower electricity bills. Some disadvantages are that they depend on the availability and intensity of sunlight, require cleaning, and have high initial cost. Solar panels are widely used for residential, commercial, and industrial purposes, as well as in space, often together with batteries. This technology is especially useful for off-grid electricity generation in rural areas. The biggest drawback of this technology is that it cannot be produced at night. Nowadays, solar panels play a prominent role to reduce greenhouse gas emissions. Thank you. Thank you, one and all. Thank you for giving this opportunity. I invite next participant is Mahita, student of political science.
Yes, ma'am.
Okay, ma. And first unmute and start your talk.
Okay, ma'am. Om Namo
Okay.
Venkateshaya. Good afternoon to the respected dignitaries and participants. I have chosen latest trends in solar cell materials. Nowadays, solar cell materials play a crucial role in energy conservation. We are depending on solar cells directly or indirectly. We are using solar cells in watches, calculators, remote lighting systems, and satellites, etc. These latest trends are beneficial to both environment and society. These trends helps us in increasing efficiency, cost reduction, sustainability, flexibility, energy access, and energy independence, etc. The emerging materials are 2D materials like graphene, nano-structured materials like nanoparticles, nanowires, earth abundant materials, lead-free perovskites, etc. Thanking you for giving this opportunity. My special thanks to Dr. K. Vijay Kumari ma'am, and my special thanks to Department of Physics for giving this opportunity. Thank you so much.
Dr. G. Padmaja, lecturer in social work, Sri Padmavati Women's Degree and PG College.
Yes,
Okay, next one. Next, I invite Pravallika Krishnan, student of Kuppam Degree College. Ma, are you on the line? Pravallika Krishnan? Pravallika Krishnan. Next, I invite next A. Lakshmi Reddy, 3rd BSc ZPC, Department of Physics, Sri Padmavati Degree College.
Yes, ma'am.
Okay, ma, start your talk.
Firstly, Om Namo Vighneswara and good afternoon to everyone.
Lakshmi,
Today
please
we are
on your video. Lakshmi, please on your video, ma.
Ma'am, actually my camera is not working, ma'am. That's why, ma'am.
Okay, okay, carry on, Talli. Okay, carry on.
Okay, ma'am. Good morning to one and all. And I'm thankful because this opportunity is actually given because of the Department of Physics. So I'm thankful to them. And today I am presenting on the crucial topic of renewable energy and its role in driving energy transition. As we all know, climate change, energy security, and sustainable development are pressing global issues. Today, I'll be exploring how solar, wind, hydro, and thermal energy can help us achieve a more sustainable future. The world is facing a crucial moment. Our reliance, our reliance on fossil fuels is contributing to climate change, air pollution, and also energy insecurity. However, this transition poses significant challenges from technological and policy hurdles to make dynamic and public acceptance. Actually, my research focuses on the role of 4 key renewable energy sources: solar source, wind source, hydro source, and also the geothermal energy in driving the energy transition. I will be examining the latest technological advancements and policy frameworks. Next, in conclusion, a renewable energy driven energy transition is not only necessary but also achievable. By 2050, we can create a more sustainable, resilient, and equitable energy system. That climate change will ensure energy access for all. I urge everyone to support and contribute to this crucial transition. Thank you for your attention and I welcome any questions you may have. Thanks for the opportunity.
Ma'am, మీరు మ్యూట్ చేసుకొని మాట్లాడుతున్నారు మ్యామ్. Okay, thank you. Thank you, Lakshmi Reddy. Now I am inviting M. Sneha, Department of Physics, Sri Padmavati Women's University. Okay, next I am inviting Raghurami Reddy, Department of Mechanical Engineering, Mohan Babu University. Sir, are you on the line, please? Raghurami Reddy, Doddipalli. Okay, next I will invite Dr. G. Balakrishna Priya, lecturer in Computer Science, Sri Padmavati Degree and PG Kalasala, TTD Tirupati.
Good afternoon to everyone. Myself, Dr. G. Balakrishna Priya from the Department of Computer Science, SPW Degree College, Tirupati. My webinar topic is Energy Efficiency Optimization in Data Centers with Technologies. So what is meant by data center? The data center is expanding rapidly due to the advancements in artificial intelligence, big data, cloud computing, and other future information technologies. This caused an enormous increase in energy usage by mounting demand for storage and processing in the cloud. Because of their large consumption and environmental impact, data centers must be energy efficient. So a green data center is a sustainable facility that provides data storage and computing resources. So building a green data center involves many factors. So that is energy efficient design using renewable energy sources, advanced cooling systems, intelligent AI algorithms that improve efficiency. So what is meant by artificial intelligence is the study of exploring computer systems that can perform functions that typically require human intelligence, including pattern recognition, experience-based learning, and problem solving. So AI and machine learning have evolved into highly efficient tools for real-time analysis of massive volumes of data, pattern recognition, and predictive power optimization. So data centers over AML advances because demand management, power delivery, and cooling infrastructure are major prospectors to influence AI and machine learning in optimizing data centers. AI optimizes IT load, electrical chain, and facility cooling through smart workload scheduling, peak shaving, and targeted thermal modeling, enhancing local optimizations and overall facility efficiency. So significant energy conservation and a greener operation are the results of the AI and ML improvements. Thank you. Thank you giving for this opportunity.
Thank you, Balakrishna Priya. Next, I am inviting Usha Pravina Vize, Department of Physics, St. Francis College for Women, Begumpet, Hyderabad.
Ma'am, Sindhuja would be presenting, ma'am.
Okay, madam. Okay. Carry on, madam. Jed Sindhuja, Department of Physics, St. Francis College for Women, Begumpet, Hyderabad, will give the talk.
One second, ma'am.
I am requesting all the paper presentees, please unmute and on your videos while presenting your paper presentation.
Good evening, everyone. I'm Sindhuja from St. Francis College for Women. My presentation is titled Sustainable Showdown, Renewable Take on Fossil Fuels, where I shall be covering topics like fossil fuels, need for renewable energy, and how to make the switch to renewable energy. Energy powers our modern world, from homes to global economies. Historically, we relied on natural resources like wood and sunlight, but since the Industrial Revolution shifted us to fossil fuels, today, technological advancements have increased energy demands, pushing us to explore sustainable options to meet our growing needs. Fossil fuels are energy sources like coal, oil, and natural gas formed by the remains of ancient plants and animals over millions of years. They are buried deep in the earth and are extracted for energy use. Their formation involves heat and pressure, converting organic matter into fuels. They have several advantages like being highly efficient and widely available, making them the backbone of global energy supply. However, they also have significant disadvantages, including contribution to air pollution, greenhouse gas emissions, and climate change. And they are non-renewable in nature, meaning they will eventually run out. But switching to renewable energy is crucial for a sustainable future. It reduces our dependence on fossil fuels, enhancing geopolitical stability by decreasing energy-related conflicts. Renewables also offer social and health benefits, such as cleaner air and water, leading to healthier communities. Economically, investing in renewable energy drives innovation, creates jobs, and promotes long-term growth. By embracing renewable energies, we not only protect our planet, but also build a more stable, prosperous, and a healthy society for the future generations. Renewable energy comes from natural sources that replenish themselves like sunlight, wind, and water. The major advantages are that it is sustainable, reduces greenhouse emissions, and decreases reliance on fossil fuels. However, there are challenges too. Initial costs for infrastructure can be very high, and some renewable sources like solar and wind can be intermittent, depending only on the weather conditions. But despite these challenges, investing in renewable energy is crucial for a cleaner, more sustainable future. These renewable energies come in various forms, like solar energy to generate which uses sunlight to generate electricity, wind energy, which captures the power of wind through turbines, biogas from organic waste, geothermal, which taps into Earth's internal heat, tidal energy that uses ocean's tides to generate power, and hydropower, which converts energy of flowing water into electricity. But how do we switch to renewable energy? Yes, it's not an easy feat, but it's not an impossible one either. Transitioning to renewable energy requires collective efforts. Raising awareness and government initiatives must support clean energy policies. Attracting investments and individuals contributing through self-made solutions are also one of the solutions. But ultimately, change begins with each one of us making sustainable choices today for a greener tomorrow. Initiatives at both home and institutional levels not only contribute to a cleaner, greener planet, but also serve to raise awareness. At my college, St. Francis College for Women, several impactful projects have been led by the EVS department and the nature club named Prakriti. These include lake cleanups, plastic-free challenges, and creative activities like art from waste. Students actively participate in volunteering days for dry and wet waste segregation, generation of compost, preparation of eco-organic cleaners, which fosters a hands-on approach to sustainability. Notably, our college has also signed an MOU with the Environment Protection Training and Research Institute to support Mission Life, which is Lifestyle for Environment, further embedding eco-friendly practices into our daily lives. We're also proud to collaborate with companies like Bisleri to install a plastic bank on campus where the plastic is segregated in the campus and collected by the company for recycling, promoting responsible waste management. Our vermicomposting pit and green corner further highlight our commitment to sustainability. Composting is a regular practice in the campus to ensure waste transformation to wealth. We engage students through exciting events and fests that emphasize eco-friendly practices. The importance of 3 Rs, reduce, reuse, and recycle, is woven into our activities, and our bottle garden is a unique space where students grow their own plants, fostering a hands-on connection with the environment. In conclusion, switching to renewable energy is a crucial task for protecting dwindling fossil fuels, advancing technology, and safeguarding our environment. It demonstrates our commitment to sustainability and the urgent need for a cleaner future. I would like to thank the management of St. Francis College for Women for their constant support and encouragement, and I extend my heartfelt gratitude to the Department of Physics at Sri Padmavati Degree College for Women for providing this valuable opportunity and a platform to showcase our work.
Thank you, Sindhuja madam, for your nice presentation. Next,
Thank
I
you.
will invite Dr. G. Padmaja, lecturer in social work, Sri Padmavati Women's Degree and PG College, and Dr. M. Pushpalata, lecturer in statistics, Sri Padmavati Women's Degree and PG College. Together, we'll give the presentation.
Good afternoon. Before my presentation, I would like to congratulate the Department of Physics, Dr. Uma Devi Madam, Dr. Jayasri Madam, Dr. Uma Maheswari Madam, and Dr. Lakshmi Sanja Madam, and Dr. Radha Krishna for their extensive effort in organizing this webinar. And I really congratulate them, and I wish them all the success and endeavors in the future. So today my topic is cultivating energy conscious among secondary grade students, a study in Tirupati. So this study is conducted in the Tirupati in order to create awareness among the secondary grade students regarding the electrical energy saving methods. The electrical energy conservation and electrical safety awareness is of utmost importance in all areas of electricity usage, be it residential, educational, commercial, or industrial. It is of great concern to bring together hundreds and thousands of students from diverse backgrounds to educate about power-saving techniques. On a wider scale, energy efficiency and conservation awareness in schools can curb the need for expanded generation capacity. And the problem statement concerning the study, we have developed that there are a lot of studies concerning this energy saving, but especially on the secondary grade students, we found that the studies are comparatively less. So we felt it is an imperative that this awareness should be cultivated from the secondary grade students, and especially also from the childhood itself, we should try to cultivate this energy saving process. The level of high energy awareness is still underdeveloped, especially among the school going children. And this should be developed since the socialization process only, so that the future generations can have the more options of energy saving process. This research addresses the critical need for increased awareness among secondary grade students, emphasizing the pivotal role of their involvement and awareness in power saving. With the growing concern for sustainable energy practices, empowering secondary grade students to contribute to energy efficiency initiatives is imperative. Thus, the research aims to investigate and understand the role of student empowerment in increasing energy efficiency through awareness. The objectives of the study are to create awareness on energy saving among secondary grade students, to assess the level of understanding on the importance of energy saving among secondary grade students, to understand the energy consumption behavior being practiced by secondary grade students, and to suggest the best practices in the schools to promote awareness among students on energy saving. The theory applied to the research is the theory of planned behavior. An experimental research had been done to assess the level of awareness regarding energy saving and also to enhance the behavior of the secondary grade students with respect to power saving strategy. A pilot study was conducted to obtain the required preliminary data for the calculation of a sample size for the primary outcome. The secondary grade students are issued power saving cards in the 14 schools selected on random basis in Tirupati, Andhra Pradesh, to assess the comparison between and after, understanding about energy efficiency, enabling a comprehensive analysis of the students' role and awareness involving in energy saving practice. A random sample of 100 students is taken for the research. The students of 6th, 7th, 8th and 9th standards were selected for the study. The study is confined only to secondary grade students as their understanding level is far better than primary grade students. The electricity saving tips for respondents is being provided on a data card over a certain period of time and created awareness to show maximum savings of power. As a proof, the participants had been attached copies of their monthly electricity bills during the study period to assess the energy consumption behavior. After the completion of filling of data card for a certain period of time, the questionnaire was demonstrated to the students consisting of the Likert scale with a 5-point rating to assess the level of understanding on the importance of energy consumption. The format of a typical five-level Likert item, for example, could be strongly disagree, neither agree nor disagree, and agree and strongly agree. Over to Pushpa.
Good afternoon to everyone. Thank you one and all for giving me this opportunity. First of all, I congratulate the Department of Physics for conducting this international conference. Analysis. The results were analyzed by using mean values to assess awareness and behavior of students. Bar and pie diagrams are also used for analyzing the data. And this figure implies the boys 55% of respondents and the girls 45% of the respondents regarding the energy saving. And this is the change habits of energy saving, identify different methods of saving, educate peers in energy saving, the willingness of the respondents. This is the bar diagram initiating the energy saving levels. And this table assessing the respondents through Likert scale, and a Likert scale is a 5-point rating system that allows respondents to express the range of opinions with 5 response options. And these are the questions regarding the energy saving. Do you feel that the energy is essential? And feeling the protection of natural resources is essential for saving more energy. Changes in day-to-day habits enables us to save more energy. The use of equipment and requiring high power energy should be minimized to some extent. And understanding the concept of energy efficiency, sharing it to the intimates to help to reach the goal, and the electrical appliances which consume less energy need to be used for daily life. Less use of power increases energy security and reduces pollution. Increase use of solar energy and plug less devices, mindful precautions enhances the energy saving, and these are the findouts. And the respondents are required to give their response to a 5 Likert scale based questions as before the table. The response to the questions is valued from 1 to 5, and with the highest level of awareness is 5 and vice versa. Later, the mean values of each items and overall mean for the 5 items are computed. Eventually, the level of awareness to each statement and the overall level of awareness toward energy saving are interpreted based on the mean range. Generally, the total average mean of every item records a value of more or less 4.40, indicating that a high level awareness of secondary grade students towards energy saving. And this can be attributed to the fact that most of the respondents are aware of the importance of energy saving with a mean of 5.0, which is situated in the mean range of very high awareness level. And come to this conclusion. To sum it up, the awareness level and energy usage behavior are assessed in this paper, and the relation between them are discussed. Overall, it is indicated that secondary grade students have high awareness level toward energy saving. However, the respondents have only past moderate behavioral level towards the energy usage of electricity. Despite that, the relationship between awareness level and behavior in energy saving is not directly linearly related. The respondents show great enthusiasm and willingness to initiate energy saving practices. Perhaps the secondary grade students are more aware on conserving electricity both in school and homes, starting by changing their lifestyle and habits as a part of energy. Thank you, ma'am. Thank you, one and all.
Thank you, Dr. G. Padmaja and Pushpalata madams, for your elaborated lecture. Next, I am inviting Miss Isha Supriya, third year BA, Department of Psychology, Sri Padmavati Degree and PG College, Tirupati. Isha Supriya, are you on the line, ma'am?
Yes, ma'am. Yes, ma'am, I am. Can you hear me,
Okay,
ma'am?
Okay.
Yes, ma'am. Good afternoon, distinguished guests and attendees. This is Isha Supriya, third BA from Sri Padmavati Women's Degree and PG College. I'm honored to discuss my paper on harnessing renewable energy, mitigating the negative impacts of climate change and global warming. There is an urgent need to transition from non-renewable to renewable energy sources, which we can all agree is a crucial step for our global future. As the world grows, so does our demand for energy. Energy is the foundation of economic and social development. However, our reliance on non-renewable resources like coal and fuel not only depletes these finite sources but also harms our environment, contributing to climate change and threatening human health. The case for renewable energy. Non-renewable energy sources, particularly fossil fuels, releases vast amount of carbon dioxide, a major contributor to global warming. This accelerates climate change, leading to severe weather events, rising sea levels, and widespread health impacts, including respiratory problems and increased disease transmission. Addressing these challenges requires a shift to renewable resources like solar, geothermal, hydropower, which offer sustainable and cleaner alternatives. Some of the key renewable sources like solar power is abundant and scalable. Projects like India's Badla solar power shows how solar energy can significantly reduce dependence on coal, providing cleaner electricity and mitigating climate change. Geothermal energy. Utilizing the Earth's internal heat, geothermal energy is a clean, reliable power source as seen in Iceland where it heats homes and workplaces. However, its use is limited to areas with suitable geological conditions. Hydropower. As the largest renewable energy source worldwide, hydropower has been pivotal in meeting energy demands. Despite challenges like high costs and environmental impact, projects like Itiapu Dam demonstrate its capacity to replace fossil fuels. The world's largest hydropower project, Three Gorges Dam in China, is an engineering marvel, providing enormous power generation capacity, flood control, and river navigation improvements. Challenges. The transition to renewable faces barriers including high initial costs, technological limitations, and public perception. Yet addressing these challenges is essential for suitable future. Investing in emerging technologies like energy storage and smart grids alongside supportive policies can make renewable energy more reliable and accessible. In conclusion, shifting from fossil fuels to renewable energy is crucial for mitigating climate change and preserving our natural resources. By embracing sustainable energy, we can ensure resilient and healthier future for future generations to come. Thank you for giving me this opportunity.
Thank you, Isha Supriya, for your brief information. Next, I will invite Okay, now I am inviting Saujanya, third BSc MPE, SPW degree and PG college. Are you on the line, ma? Sri Lakshmi. Muguruna. Sri Lakshmi. N Sri Lakshmi. Third BSc MPE. Are you on the line, ma? Okay, next I will invite P. Sandhya, second BSc Computer Honors.
Yes, ma'am.
Okay, Sandhya.
Yes,
Okay, ma,
ma'am.
on your video, ma. Unmute yourself.
Om Namo Venkateshaya. Good afternoon all. Myself P. Ratnakumari, second BSc Computer Science Department. Now I am going to presenting PowerPoint presentation on renewable energy as a primary source of energy method. I am continuing with renewable energy. Renewable energy is generally defined as energy that comes from resources which are naturally replenished on a human timeless such as sunlight, wind, rain and so on. Renewable energy, different types are there. There are many different forms of renewable energy. Solar energy, wind energy, ocean thermal, geothermal energy, biomass energy. Solar energy. Solar energy is energy the earth receives from the sun primarily as visible light and other form of electromagnetic radiation. Solar energy can be converted into electric energy by using solar plates. For example, solar cooker, solar heater, solar coal.
Wind energy. Wind energy is good, renewable, clean and free source of energy for power production. Reduce emission of greenhouse gas and other pollutant. So, ocean thermal. The ocean covers 75% of the world surface. It is the largest renewable energy source available to contribute to the security of energy supply, reduce greenhouse gas emission. House thermal, ocean thermal. Ocean covers 75% of the world surface. Enough. The ocean contains two types of energies. Ocean thermal energy conversion from the sun's heat. Mechanical energy from tides and waves. Geothermal energy. Geothermal energy is the heat from the earth. It's clean and sustainable. It found a few miles beneath the earth's surface, the down even deeper to the extremely high temperature of molten rock called magma. Biomass energy. Biomass is a renewable source of fuel to produce energy. Biomass is renewable organic material that comes from plants and animals. Thank you. Thanking you all. Thank you, ma'am. Thanking you for this opportunity.
Ma'am, you are muted.
Sorry. Okay, sorry. Okay, thank you, Ratnakumari. And I am inviting to Pavani Pavitra.
Yes, ma'am. May I audible, ma'am?
Yes, ma. Continue, ma.
Om Namo Venkateshaya. Good afternoon to everyone, ma'am. On this occasion of one day international webinar on renewable energy sources and applications. In this occasion, this is the one of the best meeting held in our college. This program was organized by Department of Physics in our college of Sri Padmavati Women's Degree and PG College. I am selected the topic is renewable energy, the difference between the renewable energy and fossil fuel energy. What is meant by renewable energy? Renewable energy is energy from renewable natural sources that are replenished on human time scale. Renewable energy are also known as green energy. The types of renewable energy are solar energy and wind power and hydropower. Bioenergy and geothermal power are also significant in some countries. In controllable renewable energy sources include dammed hydroelectricity, bioenergy, or geothermal power. And next, what is meant by fossil fuel energy? Fossil fuel energy is a carbon compound or hydrocarbon containing materials such as a coal, oil, and natural gas formed naturally in the Earth's crust from the remains of prehistoric organisms like animals, plants, and planktons. A process that occurs within geological formations. In conclusion, my analysis is renewable energy can completely replace fossil fuels in the next 30 years, but it requires the renewable energy replaces the need for the generation of electricity, which cuts greenhouse gases and helps in sustainable development. And fossil fuel have helped us build our complex industrialization societies. Fossil fuels are limited sources of energy. Almost all environmental pollution and disasters like air pollution, water pollution, and acid rains came to the fossil fuels. CO2, for example, CO2, NOx, SO2, like that. Thank you, ma'am. Thank you for giving these opportunities. Mainly, the special thanks to Dr. K. Sai Kumari Madam, the head of the Department of Political Science, and K. Vijay Kumari Madam. Thanks And special thanks to the Department of Physics madams. Thank you, ma'am, for giving your attention.
Thank you, Pavani Pavitra. And next I am inviting M. Chandralata. M. Chandralata, third BA Social Anthropology. M.
Can I start, ma'am?
Okay, ma'am. You can start.
Good evening, everyone. I am M. Chandralata from 3rd BA Padmavati Women's Degree and PG College. The topic on which I am presenting is the effect of clay bricks on non-renewable resources and the climate. The rapid growth of India's economy prompting new construction all over India. The usage of clay bricks is very significant in India for its cost effectiveness, availability, and traditional use. Despite availability of other alternatives, the production of clay bricks causes pollution at most of the stages. The clay bricks are made up of clay, laterite, and alluvials taken from the earth, which causes soil erosion, soil infertility, and disturbance in soil ecosystems. The firing of clay bricks uses coal and biomass. The quantity of coal used is much more higher than that of biomass, leading to the depletion of non-renewable resources. The majorly used kilns in India are clamp kiln, MCBTKs, moving chimney, bull trench kilns, and fixed chimney blue trench kilns. The clay brick units emits carbon dioxide, carbon monoxide, and black carbon, contributing to the air pollution. The clay bricks are fired at 900 degrees to 1100 degrees. The degradation of these clay bricks take a very long time. These clay bricks can also be reused. According to J.S. Kamayotra, Director of Central Pollution Control Board, India, clay brick units in India, the total number of clay brick units are around 1,40,000, and which produces 640 to 660 billion bricks annually. The clay consumption is around 500 million cubic meter, and the CO2 emission in this process is around 66 million metric tons. In 2016, the new guidelines for clay brick production units motivated the clay brick units to take zigzag technologies into their claims to improve the efficiency, increase coal conversion, and better production of bricks. They also motivated the clay brick production to use fly ash as the fuel, but the less availability of fly ash is not reducing the coal consumption. The coal consumption is still very much significant. The method of zigzag is showing better effect on the climate and the non-renewable resources as it consumes less coal than that of traditional kilns. So I conclude by saying that strict measures need to be taken to minimize the effect of clay bricks in India, as India consumes a lot of clay bricks and there are a lot of clay brick units in India. I thank Physics Department for conducting this seminar and also giving me opportunity. Thank you.
Thank you, Chandralata, for your nice presentation. And now I am inviting Swarna Puja, G. Swarna Puja, 3rd BSc ZPC, Sri Padmavati Women's Degree and PG College. Swarna Puja, 3rd BSc ZPC. Swarna Puja. Swarna Puja, are you on the line, please? Okay, next I am inviting Pallavi, 2nd Physics minor.
Madam, yes, madam. Can I start, madam?
Pallavi is...
Yes, madam.
Okay, ma'am.
Can I start, madam? Om Namo Venkateshaya. Om Namo Venkateshaya. Good evening to everyone. Myself, P. Pallavi. I am studying 2nd BSc Minor Physics. Today, my topic is renewable energy sources and its applications.
Renewable energy sources come from unlimited naturally replenished resources such as the sun, tides, and wind. Renewable energy can be used for electricity generation, space and water heating and cooling, and transportation. Now, renewable energy in constant comes from finite sources such as coal, natural gas, and oil. Here are a few common sources of renewable energy: solar energy, wind energy, geothermal energy, hydropower, ocean energy, bioenergy. The main source of renewable energy is hydropower. Hydropower currently is the largest source of renewable energy in the electricity sector. Renewable energy is derived from unlimited natural resources such as sunlight, wind, geothermal heat, and the movement of water, etc. Benefits of renewable energy is generating energy that produces no green gas emissions from fossil fuels and reduces some types of air pollution, diversifying energy supply and reducing dependences on imported fuels, creating economic development and jobs in manufacturing, installation, and more. Renewable energy sources like solar, wind, bioenergy, and geothermal can be used in agriculture in many ways also. These sources can help farmers increase productivity, earn more money, and improve energy security. And thanks for giving this opportunity to the Department of Physics. Thanks, madam.
Okay, Pallavi. Okay, good. Next, I am inviting T. Himabindu, second BSc Physics Honors. T. Himabindu, second BSc Physics Honors.
Yes, ma'am.
Okay, ma. You can start your presentation.
Good evening to the respected dignitaries and all the participants. Myself, T. Himabindu, studying second BSc Physics in Sri Padmavati Women's Degree and PG College, Tirupati. First of all, I would like to thank our physics department for giving me this opportunity to participate in this international webinar. Today, I'm going to talk about nuclear power, which is considered as a renewable energy resource. Energy from a source that is not depleted when used, such as wind or solar power. Any energy resource that is naturally regenerated over a short time scale and delivered directly from the sun, such as thermal, photochemical, and photoelectric. Indirectly from the sun, such as wind, hydropower, and photosynthetic energy stored in biomass, or from other natural movements and mechanisms of the environment, such as geothermal and tidal energy. Nuclear power is generated using uranium, which is a metal mined in various parts of the world. Nuclear power produces around 11% of the world's energy needs and produces huge amounts of energy from small amounts of fuel without the pollution that you get from burning fossil fuels. Nuclear power costs about the same as coal, so it's not expensive to make. It does not produce smoke or carbon dioxide, so it does not contribute to the greenhouse effect. It produces huge amounts of energy from small amounts of fuel. Nuclear power is reliable. Although not much waste is produced, it is very, very dangerous. It must be sealed up and buried for many years to allow the radioactivity to die away. Nuclear power is the use of nuclear reactions to produce electricity. Nuclear power can be obtained from nuclear fission, nuclear decay, and nuclear fusion reactions. Most nuclear power plants use thermal reactors with enriched uranium in a once-through fuel cycle. The first nuclear power plant was built in the 1950s. A major environmental concern related to nuclear power is the creation of radioactive waste such as uranium mill tailings, spent reactor fuel, and other radioactive waste. These materials can remain radioactive waste. These materials are dangerous to human health for thousands of years. Nuclear is a zero-emission clean energy source. Nuclear energy protects air quality by producing massive amounts of carbon-free electricity. Thank you for giving me this opportunity, ma'am. I'm done.
Thank you, Himindu. You were given the nice presentation. And next, I am inviting K. Indraja, second BSc Mathematics Honors. K. Indraja. Okay, ma. You
Om
can
Namo
start the.
Om Namo Venkateshaya. Good evening to all. I am K. Indraja from 2nd BSc Honors Mathematics with minor Physics.
Today my topic is about latest trends in solar cell materials. First, I want to introduce about solar cells. Solar cells, also known as photovoltaic cells, are devices that convert sunlight directly into electricity. The efficiency, cost, and performance of solar cells are largely determined by the materials used in their construction. And I want to tell about key factors in material selection used in solar cells. Efficiency. The ability of the solar cells to convert sunlight into electricity. Higher efficiency means more electricity is generated for a given area. Cost. The cost of materials are and manufacturing process can significantly affect the overall cost of solar power. Stability and durability. Solar cells need stand with environmental conditions such as UV radiation, moisture, and temperature fluctuations for long periods. And flexibility. Materials that allow for flexible solar panels open up new possibilities for integration into various surfaces such as curved roofs or even wearable devices. My topic is about the trends in solar cell materials. The field of solar cell materials is rapidly evolving with new trends focusing on improving efficiency, reducing cost, and enhancing the sustainability of solar energy. Here are some of the latest trends in solar cell materials. First one is the bifacial solar cells. Dual-sided light absorption. Bifacial solar cells are designed to absorb light from both the front and back surfaces, allowing them to capture reflected light and improve overall energy generation. And second one is the passivated emitter and rare cell technology. Market dominance. Passivated emitter and rare cell technology has become the new standard in the solar industry. PARC cells use a passivation layer on the rare surface to reduce electron recombination, improved in performance, especially in low light. And the third one is the quantum dot solar cells. This is the next generation materials, quantum dot solar cells, which use nanoscale semiconductor particles are being so subtle, potential to surpass the Shocky Quasar limit to conventional solar cells. And the fourth one is the sustainable and recycling. This is eco-friendly materials. There is a growing trend towards using more sustainable and environmental friendly materials in solar cell production and recyclability. The solar industry is increasing focusing on the recyclability of solar panels. And the fifth one is the advanced manufacturing techniques, printing technology. Techniques such as inkjet and roll-to-roll printing are being developed to manufacture solar cells at a lower price and with greater scalability. And the 3D printing. 3D printing is also being explored as a way to create custom solar cells and modules. And the sixth one is the photovoltaic integrated products. This is the solar fabrics and wearables. Flexible solar materials are being used to create solar powered fabrics and wearable devices, enabling new applications in personal electronics and off-grid energy solution. According to my conclusion, these trends highlight the dynamic nature of solar cell research and development, with ongoing innovation aimed at making solar energy more efficient, affordable, and widely applicable. Special thank to our minor physics department. Ma'am, thank you so much for giving me opportunity. Thank you, ma'am.
Thank you, Indraja. Thanks for your elaborated presentation. Next, I am inviting Nagalakshmi Vavilla. Are you on the line? Nagalakshmi Vavilla. Next, I am inviting Vishnu Priya. Vishnupriya. Meere rasa. Next,
Yes,
I am
ma'am.
inviting Vishnupriya.
Madam.
Are you on the line?
Yes, ma'am.
Okay, ma'am. Okay, ma'am. You can start the presentation.
Good evening to all. I am M. Vishnupriya, studying third year BA HPSA. Today my webinar topic is renewable energy resources. What is renewable energy? Renewable energy is energy derived from natural sources that are replenished at a higher rate than they are consumed. Sunlight and wind, for example, are such resources that are constantly being replenished. Renewable energy sources are plentiful and all around us. Fossil fuels, coal, oil and gas, on the other hand, are non-renewable resources that take hundreds of millions of years to form. Fossil fuels, when burned to produce energy, and cause harmful greenhouse gas emissions such as carbon dioxide. Generating renewable energy creates far lower emissions than burning fossil fuels. Transitioning from fossil fuels, which currently account for the lion's share of emissions, to renewable energy is key to addressing the climate crisis. Renewable are no cheaper in most countries and generate 3 times more jobs than fossil fuels. Thank you for giving me this golden opportunity, madam.
Okay, ma. Thank you, Vishnupriya. And next, and one small information, I am requesting you, all the participants, please turn on your videos. Next, I am inviting K. Kalpana, second BSc Chemistry Honors.
Ma'am, I can start, ma'am.
Oh, okay, ma'am. You can start.
Good evening to everyone. Good evening, ma'am. First of all, myself introducing. My name is Y. Kalpana, second BSc Chemistry and minor Physics. So, today in my topic is renewable energy development and strategies. Renewable energy has so many advantages. By using the renewable energy sources, we reduce uses the fossil fuels. Renewable energy can help the mitigating climate change and improve the environmental health. In this renewable energy is the so many benefits. So the renewable energy is resources are the important because they can be replenished in the naturally over time. The developments of the renewable energy. So this including improving the energy production efficiency, saving the energy and demand and the replacing the fossil fuels with the renewable energy resources. This can include the tax and financial policies that encourage the development and use of the renewable energy. This include the using the smart grids, energy efficient applications and building designs to reduce the every energy consumption. So the combining the renewable energy resources like the solar and wind can help the addresses the intermittency of one sources and the improve grid stability. Small hydropower plants can help the increase the rural electrification, improve the reliability of the country's power system. International challenges. So the climate change due to the release of the carbon dioxide in the atmosphere. Developing the economies are the transforming from the agriculture to the industrial base in the economies. This result in the growth energy used as the manufacture of the domestic product relies increasingly on the industrial production. Expansions of the urbanization and modern cities shows the change in the energy consumption patterns. Renewable energy is developments are still dependent on the foreign donors and the investors. Renewable energy can reduce the carbon emissions and the air pollution from the energy production. Renewable energy can help the diversity energies and supply and reduce the dependence on important fuels. Renewable energy can create the jobs in manufacturing installation and other areas. Renewable energy can improve the reliability, security and resilience of the power grid. Renewable energy can help the lower energy cost. Thanking you. Thank you, ma'am. Thanking this giving opportunity.
Okay, thank you, Kalpana. Next, I am inviting Dr. Y. Jayashree, lecturer in physics, SPW Degree and PG College, TTD Tirupati.
Thank you, Dr. G. Lakshmi Sandhya. Now I am going to present my paper on the topic renewable energy versus fossil fuels. I am going to present this along with my colleagues, Dr. YB Kishore Kumar and Dr. G. Suresh Babu, lecturer in physics, Government Degree College, Puttur, and head of the Department of Physics, Mohan Babu University, Sri Vidyaniketan, Rangampet. Now, I am going to present the energy sources are vital for the economic growth of any country. Food, shelter, and clothing, the three essential requirements of mankind, and hence the quality of life essentially depend on, to a large extent, on the energy resources of the country. There is ever-growing demand for more and more utilizable power due to increase in population, urbanization, and industrialization. Presently, about 80% of the energy demand is met through fossil fuels. There are fast depleting, and it is expected to that in another 100 to 200 years, these sources get exhausted. There is ever-growing concern on the impact of increased emission of greenhouse gases on environment due to indiscriminate usage of fossil fuels. Thus, there is an imperative need to accelerate the development of renewable energy sources like solar, wind, bioenergy, etc., initiated a few decades back. Among renewable energy sources, solar energy is an attractive option for a tropical country like India. It is a perennial and pollution-free source. Earth receives 1.7 into 10 power 11 megawatts of power from the sun, which is 20,000 times larger than the total energy consumption rate on the earth. Even if a fraction of this energy can be effectively utilized, the energy problem of the country could be mitigated to some extent. As we move towards a zero carbon future, renewable technologies are becoming widely popular energy sources throughout the world. So countries, corporations, and individuals are adopting clean energy for several great benefits, from reduced air pollution to financial savings. So renewable energy has multiple advantages over fossil fuels. Let us discuss some of the advantages and disadvantages of renewable energy versus fossil fuels. Renewable energy sources are ever-ending sources, pollution-free, economically viable, low earth maintenance requirements. So whereas fossil fuels are materials containing carbon compounds or hydrocarbons such as coal, oil, and natural gas. So fossil fuels are considered as non-renewable sources. These are the materials formed naturally in the Earth's crust from the remains of organisms. So these compound mixtures can be burned as a fuel for human consumption to provide heat for direct use, such as for cooking or heating, to power heat engines such as steam or internal combustion engines that can propel the vehicles, or to generate electricity via steam turbine generators. Some fossil fuels are further refined into derivatives such as kerosene, gasoline, and diesel. The large-scale burning of fossil fuels causes serious environmental damage. So over 70% of the greenhouse gas emission due to human activity in 2022 was CO2 from burning them. Therefore, there is a net increase of many billion tons of atmospheric carbon dioxide per year. Although methane leaks are significant, the burning of fossil fuels is the main source of greenhouse gas emissions, causing global warming and ocean acidification. Additionally, most air pollution deaths are due to fossil fuel particulates and noxious gases. Whereas renewable energy, which is a green energy, it is the energy from renewable natural resources that are replenished on a human time scale. The most widely used renewable energy types are solar energy, as I discussed earlier, wind power and hydropower. Bioenergy and geothermal power are also significant in some countries. Renewable energy installations can be large or small and are suited for both urban and rural areas. Renewable energy is often deployed together with further electrification. This has several benefits. Electricity can move that and vehicles efficiently and is clean at the point of consumption. Variable renewable energy sources are those that have a fluctuating nature, such as wind power and solar power. In contrast, controllable renewable energy sources include dam hydroelectricity, bioenergy, or geothermal powers. Renewable energy sources such as solar and wind power have seen significant cost reductions over the past decade, making them more competitive with traditional fossil fuels. The main motivation to replace fossil fuels with renewable energy sources is to slow and eventually stop the climate changes, which is widely agreed to be caused mostly by the greenhouse gas emissions. In general, renewable energy sources cause much lower emission than fossil fuels. Thus, a lot of research and development efforts on renewable energy sources, for example, solar energy materials and devices, are very much essential. So, with this brief description, on this renewable energy versus fossil fuels, I conclude my topic. Thank you for giving me the opportunity. Now I request.
Thank you. Thank you, madam. Thank you, Jayashree madam, for your nice presentation.
Now I request the chairperson of this session, Dr. Tarna Teja madam, to give her brief report on this second scientific session.
Yes, madam. We have now concluded our afternoon session presentations. Here is a brief overview of what we have covered in the afternoon. To start, Chandrasekhar, a research scholar, discussed hydrogen fuel production technologies and their role in sustainable development, and mentioning the approaches and future prospects for this promising renewable energy sources. And next, Dr. Sunita focused on energy saving in urban and rural areas. And she also mentioned various fossil fuels and mentioned the strategies to reduce carbon emissions. And Dr. Kumudini provided an overview of sustainable energy sources and highlighting India's progress as a global leader in the solar energy. And Dr. Uma Devi outlined the advantages of solar panels such as renewable energy and low operating costs, as well as the disadvantages like high initial cost and weather dependency. She also mentioned the various applications and including the residential and commercial use. Next, Dr. Balakrishna Priya discussed energy consumption in data centers and the development of green data centers. She highlighted the algorithms that improve efficiency and the use of artificial intelligence and machine learning for optimizing energy use. Next, Dr. Padmaja and Pushpalata focused on cultivating energy consciousness among secondary grade students, and they mentioned the importance of education on electricity and energy conservation, aiming to raise awareness and mentioning the significance of energy saving in future generations. And then Dr. Jayashree and her group addressed the energy consumption and the transition to a zero carbon future. And she mentioned that the renewable energy offers significant advantages over fossil fuels, including the reduced carbon emissions and enhanced sustainability, making it is crucial for achieving the low carbon energy landscapes. We also have presentations of students from different universities like Mahita, Lakshmi, Ratnakumari, Chandralata, Pallavi, Indraja, Vishnupriya, and Kalpana. They all discussed on the topic, that is impact of renewable energy on climate change and global energy trends.
Sindhuja discussed the importance of switching from fossil fuel to renewable energy sources, and she covered various types of renewable energy strategies for transitioning to these sources. And she mentioned that her college's green initiatives, including the collaborations with the companies and promoting waste management. And next, Isha Supriya also discussed the transition from fossil fuels to renewable energy sources. She addressed that global thermal energy and exploring techniques to replace or reduce the cost, as well as the challenges occurred with these energy sources. Then Himabindu discussed the importance of nuclear power as a renewable energy source and its advantages such as low greenhouse gas emissions and high energy output, including the safety concerns and the radioactive waste, evaluating the role in the future energy mix. That's all the overview of about the presentations from the afternoon session. And thank you very much to all the presenters from the forenoon and afternoon sessions for their contributions to this webinar. Thank you very much.
Thank you. Thank you, Dr. Tarun Teja, for your nice and brief report on the scientific sessions of this afternoon. Thank you so much. And I request our HOD Madam, Dr. C. Uma Devi, to give the overall report of this today's one-day international webinar.
Thank you, Jayashree. Being the organizing secretary of this webinar, I feel it privileged to present a brief report on this webinar. The Department of Physics, Sri Padmavati Women's Degree and PG College, TTD Tirupati, organized this international webinar on renewable energy sources and its applications today. Sri J. Shyamalarav Garu, IAS Executive Officer, is the chief patron. Srimati M. Gautami Garu, IAS Joint Executive Officer, Health and Education, Dr. Y. Nagaraj Naidu Garu, Devasthanam Educational Officer, are the patrons. Dr. T. Narayanamma, Principal of this college, is the convener for this webinar. Myself, Dr. C. Uma Devi, HOD, Department of Physics, is the organizing secretary. Dr. Y. Jayashree, Dr. D. Uma Maheswari, Dr. G. Lakshmi Sanja, Dr. J. Radhakrishna are the organizing committee members. The program started with the welcome address, followed by the message by the convener of the webinar, Dr. T. Narayanamma Garu. A total number of over 250 participants participate actively in this webinar. In the forenoon session, the invited talk was given by the resource person, Dr. P. Jeevan Kumar, Assistant Professor, University of Japan, on evolution of battery technology from traditional to solid-state innovations. It is highly appreciable and informative. Sir's presentation offered a thorough overview of evolution of early electrochemical cells into the sophisticated systems we use today, with a focus on lithium-ion batteries and their advancement towards solid-state designs. The presentation started with examining the historical progression of battery technologies, highlighting key milestones that have influenced modern energy storage solutions. The discussion then extended to transitions to the evolution of lithium-ion batteries, covering their fundamental principles, improvements in performance, and the growing demand for higher efficiency and safety. Sir also addressed the global competition for securing strategic minerals critical to the future of energy storage. Later, the scientific sessions for the forenoon session started and chaired by Dr. Tarun Teja, specially appointed researcher, Osaka University, Japan. 20 papers were presented during this morning session. The invited talk in the afternoon session by the resource person, Dr. U. Tirupati, Assistant Professor, University of South Korea, on thin film solar cells and overview, is very much informative. In his presentation, he explained the fundamentals of thin-film solar cells, providing a comprehensive overview of their unique properties, advantages, and challenges compared to traditional silicon-based solar cells. Sir also discussed various types of thin-film technologies such as amorphous silicon, cadmium telluride, and copper indium gallium selenide, discussing their fabrication process, efficiency levels, and applications. Additionally, Sir also covered the fabrication process of thin film solar cells that were developed in their laboratory. Second scientific session started in the afternoon, chaired by Dr. Taruna Teja, and 22 papers were presented. She gave a brief report on these two scientific sessions. Hence, herewith I put forth this brief report on today's webinar on renewable energy sources and its applications. Thank you, one and all.
Thank you, madam. Thank you for your very detailed report of today's one-day international webinar on renewable energy sources and applications. Thank you very much, madam. Now, I request Dr. J. Radhakrishna, Faculty of Physics, to give a vote of thanks of this program.
Thank you, Jessica, madam. Good evening, everyone. It has been such an honor to be a part of this wonderful event. On behalf of our physics department, I, Dr. J. Radhakrishna, would like to extend my heartfelt gratitude to our esteemed Executive Officer, Sir J. Shamal Rao Garu, IAS, Joint Executive Officer, Srimati M. Gautami Ma'am, IAS, and Devasthanam Educational Officer, Dr. Y. Nagaraj Naidu, Sir. I would like to express our sincere gratitude to our TTD management for encouraging and giving permission to organize this webinar today in a smooth way. Thank you very much to our management. I would like to express our sincere thanks to our resource person, Dr. P. Jeevan Kumar, Assistant Professor from Japan, Dr. U. Tirupati, Assistant Professor from Korea, and Dr. J. Tarun Teja Ma'am from Japan for taking time to share their knowledge and also for their informative, insightful presentation today. The information shared on renewable energy sources and applications has incredibly valuable and will certainly help the new and young generation. Thank you very much, sirs and madam. I would like to extend our gratitude to our beloved Principal Madam, Dr. T. Narayanamma Garu, who convened this webinar in a well-organized, systematic way with her continuous, consistent encouragement, study support in each and every footprint of this webinar. Thank you very much, ma'am. It goes without saying our sincere and deep gratitude to our organizing secretary, our HOD ma'am, Dr. C. Umadevi, without whose support this program would not have taken beautiful path today. Thank you very much, madam. I would like to extend our heartfelt thanks to each and every one of you and appreciations to all the attendees from the corners of the world. Thank you so much for joining us today for this insightful webinar. I extremely extend our thanks to Satwa Infotech Solutions CEO K. Girish Kumar Garu and his team, Mr. N. Yashwant Garu, for their technical support to run this webinar in a smooth way, right from the beginning to the till end today. Thank you so much, sir. My sincere thanks to all the faculty of various departments and students who handled the event with their timely support. I thank all the faculty members of Department of Physics of this college in making this webinar a grand success. Finally, I would like to thank all of you present here for making the time to be with us today and helping in making this event a grand success. Thanking you one and all. Thank you very much, ma'am.
Thank you, Radhakrishna. So, one information and one request to all the participants. that we have sent a feedback form to your mails. So please go through your mail and send the feedback forms. And e-certificate will be issued to all the participants who are present today, and it will be sent to you within a week. Thank you. Thank you for being with us. So please check your mails and fill the feedback forms and send to the same mail ID. Thank you. We'll stop this program with the national anthem. Jai Hind.